The world feels solid. Light fills a room. Surfaces hold their shape. Sounds arrive from clear directions, carrying meaning without effort. Objects remain where they were left. Time moves forward in a steady, familiar way. Nothing about ordinary experience suggests uncertainty. Reality feels immediate, continuous, and reliable, as though it simply presents itself exactly as it is. And yet beneath that calm surface, science has been quietly uncovering something unexpected. The brain does not passively receive the world. Physics does not describe solid objects in the way intuition suggests. At the smallest scales, matter behaves more like possibility than substance. At the larger scales, space and time bend and stretch. What feels direct turns out to be inferred. What feels stable turns out to be assembled. The reality experienced each moment may not be the reality that exists independently of observation, measurement, or interpretation. This raises a gentle but profound question. If experience is constructed, if perception is a model, and if the physical world itself resists simple description, then what does it really mean to say that something is real? This is not a question meant to unsettle or disturb. It is an invitation to slow down, to look carefully, and to explore how reality is understood by neuroscience, physics, and careful inquiry, one quiet layer at a time. Welcome to the Sleepy Scientist. If this is the kind of question that helps you unwind, consider liking the video and subscribing for more calm explorations of science. And wherever this moment finds you, whether listening from a familiar room or a distant place, feel free to share where you are watching or listening from, as the idea of reality often begins exactly where experience happens. The world feels solid in a way that rarely invites doubt. When a hand reaches out, it meets resistance. When a foot presses against the ground holds firm. Light arrives from predictable directions, outlining edges and surfaces with quiet reliability. Sounds carry meaning through the air without effort. Objects remain where they were placed. Causes lead to effects with comforting regularity. Nothing about ordinary experience suggests that reality is fragile, uncertain, or incomplete. From the moment of waking, the world presents itself as stable and continuous. A room does not flicker in and out of existence. A table does not soften when looked away from. Gravity does not pause to renegotiate its terms. Even change follows rules. Ice melts, shadows move, day gives way to night. Reality behaves itself. It feels dependable enough that questioning it seems unnecessary, even a little strange. This sense of solidity is not accidental. Human perception evolved to deliver a usable world, not a perfectly faithful one. In perceptual psychology, this is sometimes described as ecological validity. The idea that sensory systems are tuned to what matters for survival rather than what exists in full detail. Seeing the exact electromagnetic structure of a wall is unnecessary. Knowing that the wall will stop forward motion is sufficient. Hearing the molecular vibrations of air is less useful than recognizing a voice or a threat. The brain prioritizes reliability over completeness. Evolutionary biology reinforces this point. Organisms that interpreted their environment quickly and consistently were more likely to survive and reproduce. There was no advantage in perceiving every ambiguity, uncertainty, or hidden structure of the world. Certainty, even approximate certainty, kept bodies intact and lives moving forward. Over millions of years, nervous systems became very good at presenting a world that feels direct, immediate, and trustworthy. As a result, experience arrives already organized. Surfaces appear smooth or rough. Objects appear separate from one another. Space appears continuous. Time appears to flow forward at a steady pace. These impressions do not feel constructed, they feel given. The world seems to announce itself without mediation, as though perception were a clear window rather than a carefully assembled interface. This is sometimes referred to as naive realism, the intuitive belief that the world is experienced exactly as it is. In everyday life, naive realism works remarkably well. Doors open when pushed, fire burns when touched, distance matters, speed matters, reality pushes back in predictable ways. From this perspective, the idea that reality might be indirect or constructed feels unnecessary at best and indulgent at worst. The brain reinforces this confidence by smoothing over uncertainty. Small gaps in vision are filled in automatically. Rapid eye movements are hidden from awareness. Slight inconsistencies in sound or touch are resolved without conscious effort. Memory stitches moments together into a seamless flow. The result is a world that appears continuous, even though perception is sampled, filtered, and interpreted in fragments. Neuroscience shows that this process is active rather than passive. Signals from the eyes, ears, and skin do not arrive in the brain labelled with meaning. They arrive as electrical impulses, patterns of activity that must be interpreted. Yet none of this effort is felt. Experience arrives already whole. A cup is simply a cup. A sound is simply a sound. Reality appears finished by the time awareness encounters it. This efficiency creates trust. The world feels reliable because it usually is, at least at the scale of daily life. A chair does not suddenly dissolve into probabilities. The floor does not forget how to support weight. Even when surprises occur, they do so within boundaries. A glass may shatter, but it still obeys gravity. A storm may arrive, but it still follows physical laws. Reality may be dramatic, but it is rarely arbitrary. This reliability encourages a quiet assumption that feeling real and being real are the same thing. If something appears solid, stable, and consistent, then it must simply be that way. The success of everyday interaction reinforces this belief. Tools work, technology works, predictions work, planes stay in the air, bridges stay standing. From this perspective, questioning the nature of reality can seem detached from practical concerns. And yet, this confidence rests on a very specific level of description. At human scales, reality behaves in ways that align with intuition. Objects are large compared to atoms. Speeds are slow compared to the speed of light. Forces balance in familiar ways. Under these conditions, the physical world behaves approximately as it appears. Solidity emerges from electromagnetic interactions between atoms. Stability arises from energy minima. Continuity is an effective approximation. The world is not lying, it is simplifying. This distinction matters. There is a difference between a useful description and a complete one. A map that omits every grain of sand is still an excellent map. A weather forecast that smooths out microscopic turbulence can still guide decisions. In the same way, everyday experience provides a version of reality that is accurate enough to navigate, even if it leaves out enormous amounts of underlying structure. The purpose of beginning here is not to undermine trust in experience, it is to respect it. Any serious discussion of reality must start with the world as it is lived. Without this grounding, questions about perception, physics, or consciousness float free of meaning. The solid world of daily life is not an illusion to be dismissed. It is the reference point against which all deeper inquiry must be measured. At the same time, small hints of complexity already appear within ordinary experience. Optical illusions show that perception can be misled. Expectations shape what is noticed and what is ignored. Fatigue alters judgment. memory edits the past. These effects are usually subtle enough to ignore, but they reveal an important fact. Experience is not a direct imprint of the world. It is a negotiated outcome between external conditions and internal processes. This does not mean that the world is unreal. It means that reality, as lived, is mediated. Feeling real does not automatically guarantee completeness. Solidity may be an emergent property rather than a fundamental one. Stability may be a pattern rather than a substance. These ideas need not be threatening. They are simply observations about how experience works. Humor occasionally helps here. The brain, for all its sophistication, is operating on limited information. It does not know everything. It guesses. It fills in. It smooths over rough edges. And most of the time, it does an excellent job. The fact that this system allows for modern science, engineering, and quiet moments of reflection suggests that it is doing something right. This first step is about acknowledging how convincing the world is before asking how that conviction is produced. The everyday sense of reality is not something to escape from. It is something to understand. Only by appreciating how stable, reliable, and solid the world feels can deeper questions be asked without drifting into abstraction. The ground beneath experience feels firm for a reason. That firmness will remain the reference point, even as layers are slowly examined. Reality, as it appears, is not wrong. It is simply one level of description among many, and it is where understanding begins. The world does not arrive in the brain as a complete picture. What arrives instead is a scattered collection of signals. Tiny electrical changes travel along nerve from the eyes, the ears, the skin, the nose, and the tongue. On their own, these signals have no color, no sound, no texture, and no meaning. They are patterns of activity, variations in timing and intensity, fragments of information stripped of context. Everything that feels rich, continuous, and immediate must be assembled from this limited input. This is because sensory systems are not designed to show the world as it is in full. They are biological filters. Each sense samples only a narrow slice of what exists, ignoring most of the physical information surrounding the body at any given moment. Perception is selective by necessity. There is simply too much going on for a nervous system to register it all. Vision is a clear example. Human eyes are sensitive to a very small portion of the electromagnetic spectrum. What is seen as visible light occupies a thin band between longer wavelength infrared radiation and shorter wavelength ultraviolet radiation. Radio waves pass through the body unnoticed. X-rays stream through space without leaving a trace in experience. Even within the visible range, detail is uneven. Sharp resolution exists only in a small region at the center of vision. Everything else is blurred, filled in, and stabilized by the brain. Hearing is similarly constrained. The human auditory system responds to vibrations in air within a limited frequency range. Very low-frequency sounds move through the environment unheard. Very high-frequency sounds, audible to bats or dolphins, pass by unnoticed. Loudness, pitch, and direction are not properties of sound itself, but interpretations built from how hair cells in the inner ear respond to pressure changes. Touch, often assumed to be the most direct sense, is also selective. The skin contains different receptors for pressure, temperature, vibration, and pain, each tuned to specific thresholds. Some changes are detected immediately, others never reach awareness. A constant pressure fades from attention. A steady temperature becomes background. The nervous system focuses on change, contrast, and potential threat, not on faithful recording. These limits are not flaws. They are design features shaped by evolution. Sensory systems evolved to highlight what matters for action. The goal was never completeness. The goal was usefulness. Perception delivers a version of the world that supports movement, decision-making, and survival, even if that version omits vast amounts of physical detail. The idea that perception is indirect is not new. In the 19th century, the physicist and physiologist Hermann von Helmholtz argued that perception involves unconscious inference. According to Helmholtz, the brain uses sensory input as evidence from which it infers the most likely state of the external world. What is experienced is not a direct imprint of reality, but a conclusion reached by the nervous system. This was a radical idea at the time. It suggested that experience is an interpretation, not a mirror. Helmholtz showed that perception depends on prior knowledge, expectation, and learned associations. The same stimulus can produce different experiences depending on context. The brain fills in gaps, resolves ambiguity, and settles on the most plausible explanation, usually without awareness. Modern neuroscience has strongly reinforced this view. Sensory information arriving at the brain is incomplete, noisy, and delayed. Signals from the eyes take tens of milliseconds to reach visual cortex. Auditory signals arrive with their own delays. Touch arrives through multiple pathways with different speeds. To create a coherent experience, the brain must actively integrate and align this information, correcting for timing differences and filling in missing data. This construction happens constantly. When looking around a room, the eyes jump rapidly from point to point several times each second. During these movements, visual input is briefly suppressed, yet experience feels continuous. The brain edits out the gaps. When blinking, vision disappears for a fraction of a second, but awareness never notices the absence. Experience feels seamless because the brain ensures that it does. Color provides another example. Color is not a property of objects themselves. It arises from how different wavelengths of light stimulate cone cells in the retina, and how those signals are compared and interpreted by the brain. The same physical surface can appear different under different lighting conditions, yet perception tends to preserve color constancy. The brain compensates for illumination changes to maintain stability, even when that stability requires distortion. Sound localization works in a similar way. The brain estimates the direction of a sound by comparing tiny differences in timing and intensity between the two ears. These differences are often smaller than 1,000th of a second. From this limited information, a stable auditory space is constructed. Sounds appear to originate from precise locations, even though no single sensory receptor contains that information. All of this reveals a defining principle of perception. Experience is inferred, not delivered. The brain is constantly solving a problem. Given limited data, what is the most likely explanation for what is happening out there? This process is fast, automatic, and usually accurate enough to trust. This does not mean that perception is arbitrary or imaginary. The external world strongly constrains what can be perceived. A wall cannot be experienced as empty space if it reliably stops motion. Fire cannot be experienced as harmless if it reliably damages tissue. The brain's interpretations are shaped by real, persistent regularities. But the path from physical cause to conscious experience is indirect. Recognizing this is the first quiet step away from naive realism. The everyday certainty established earlier remains valid, but it gains a deeper context. The world feels direct not because it is directly accessed, but because the brain has become extremely good at hiding its own work. The construction is invisible from the inside. There is a subtle humor in this arrangement. The brain, a piece of the physical world, spends its time constructing a usable version of the physical world for itself, while never showing the scaffolding involved. It presents conclusions without footnotes. Experience feels simple, because complexity has been carefully managed behind the scenes. Importantly, this does not undermine trust in perception. It explains why perception is reliable within its limits. By filtering information and emphasizing stability, the brain creates a world that can be navigated without constant uncertainty. The cost of this efficiency is incompleteness, not falsehood. Perception, then, is not a window through which reality is seen. It is an interface, shaped by biology, physics, and history. It shows what matters, hides what does not, and smooths over ambiguity to keep experience coherent. The solid world of daily life remains, but it now sits within a richer understanding. Reality has not changed. What has changed is the recognition that experience is an interpretation layered on top of it. The certainty of everyday perception still holds, but it rests on an active process rather than passive reception. The brain does not open a window onto the world. It builds a world it can live in. The brain does not wait passively for the world to announce itself. Instead, it is constantly anticipating what will happen next. Long before sensory information arrives, the brain is already preparing an explanation. It predicts the shape of objects, the continuation of sounds, the weight of familiar items, the direction of motion, and the likely outcome of ordinary actions. Perception begins not with input, but with expectation. This idea sits at the heart of a modern framework in neuroscience known as predictive processing. According to this view, the brain functions less like a camera and more like a forecasting system. Its primary task is not to record the world, but to predict it as efficiently as possible. Sensory input is then used to correct those predictions when they are wrong. At any given moment, the brain is running a quiet internal simulation of the world. It generates hypotheses about what should be out there, based on past experience, context, and learned regularities. Incoming sensory signals are compared against these expectations. When the signals match the prediction, very little changes. When they differ, an error is detected and the model is adjusted. This process is often described using Bayesian inference, a mathematical framework for updating beliefs in light of new evidence. In simple terms, Bayesian inference formalizes how a system combines prior expectations with incoming data to arrive at the most probable explanation. The brain does not need to perform explicit calculations to behave this way. The logic is built into neural dynamics shaped by evolution and learning. The key idea is that perception reflects a balance between what is expected and what is sensed. When sensory data is clear and strong, it can override expectations. When data is weak, noisy, or ambiguous, expectations play a larger role. This explains why perception is stable in familiar environments and more uncertain in unfamiliar ones. The brain leans on what it already knows when information is limited. This approach helps explain why perception is fast. Reacting to raw sensory data alone would be too slow. By predicting what is likely to occur, the brain can prepare responses in advance. Catching a falling object, understanding speech in a noisy room, or navigating a familiar space all rely on anticipation. Prediction reduces the need to process everything from scratch. A prominent contemporary formulation of this idea is associated with the neuroscientist Carl Friston and what is known as the free energy principle. At a high level, this principle proposes that biological systems maintain their organization by minimizing surprise. In this context, Surprise means a mismatch between what is expected and what is encountered. By continually updating internal models to reduce prediction error, the system stays within viable states. Despite the technical name, the core intuition is simple. A system that consistently fails to predict its environment will fall apart. A system that predicts well remains stable. From this perspective, perception, action, and learning are all aspects of the same process, reducing uncertainty about the world. In perception, this means that experience reflects the brain's best current guess about what is causing sensory input. That guess is shaped by prior knowledge, recent context, and long-term learning. Sensory signals do not dictate experience on their own. They constrain and refine an ongoing prediction. This explains why perception can be so convincing even when it is incomplete. The brain does not wait for perfect information. It commits to an interpretation as soon as it is good enough. This commitment gives experience its clarity and immediacy. A face is recognized instantly. A word is understood before the sentence is finished. The world feels present because predictions are constantly being confirmed. It also explains why perception can sometimes be wrong in systematic ways. When expectations strongly outweigh incoming data, the brain may perceive something that is not there or miss something that is. Optical illusions often exploit this balance. They create conditions where the brain's usual predictions lead to an incorrect but stable interpretation. Importantly, this does not mean that perception is careless or sloppy. Prediction is constrained by reality. If predictions consistently fail, they are revised. Touching a hot surface overrides expectations quickly. Falling disrupts predictions immediately. The physical world exerts a strong corrective influence. The brain cannot simply imagine any reality it wants. What changes is how perception is understood. Instead of being a direct readout of the world, it becomes an active process of hypothesis testing. Experience is not delivered, it is inferred. The brain asks, silently and continuously, what is the most likely explanation for this pattern of input right now? This deepens the earlier understanding of sensory limits. Sensory systems do not merely filter information. They provide evidence to support or challenge predictions. The brain fills in the rest. This division of labor explains why experience feels complete, even when sensory data is sparse. Consider vision again. The image formed on the retina is two-dimensional, inverted, and full of gaps. Blood vessels block parts of the visual field. The optic nerve creates a blind spot, yet none of this appears in experience. The brain predicts continuity and fills in missing information so effectively that the construction remains invisible. Hearing works similarly. Speech is often fragmented by noise, overlapping sounds or incomplete signals, yet meaning is reconstructed effortlessly. The brain predicts likely words and phrases based on context and language knowledge. When a sound is unclear, the most probable interpretation is selected, often without awareness. This predictive approach also explains why context matters so much. The same sensory input can produce different experiences depending on expectation. A shadow can be seen as a harmless shape or a threatening figure depending on circumstances. A sound can be interpreted as speech or noise depending on context. Prediction shapes interpretation. There is a quiet elegance to this system. By predicting the world, the brain reduces the amount of information it needs to process. Only differences matter. Confirmations are cheap. Errors are informative. This efficiency allows complex organisms to operate in real time without being overwhelmed by detail. Gentle humor sometimes helps here. The brain is essentially running a very fast, very opinionated guessing game. Most of the time it guesses correctly enough to keep things running smoothly. When it guesses wrong, it corrects itself, usually without drawing attention to the mistake. The result is a world that feels immediate and stable, even though it is assembled moment by moment. Perception becomes a best estimate rather than a photograph. It is anchored in reality but shaped by expectation. It is reliable without being complete. Understanding the brain as a prediction machine does not make experience feel less real. It explains why experience feels the way it does. The solidity of the world established earlier remains intact. What changes is the appreciation of how that solidity is achieved. The brain does not open a window onto reality. It builds a model that works. That model is continuously tested, updated, and refined through interaction with the world. Sensory input keeps it honest. Prediction keeps it efficient. This view brings perception into alignment with the broader themes already emerging. Sensory limits restrict what can be known directly. Interpretation fills in the rest. Prediction ties it all together. Experience becomes a dynamic negotiation between what is expected and what is encountered. Reality in this framework is not passively observed, it is actively inferred. The world pushes back when predictions fail, ensuring that perception remains grounded. Within those constraints, the brain delivers a coherent, stable experience that feels direct, precisely because the underlying work is hidden. What is experienced is not reality in its entirety. It is the brain's best current explanation of reality, shaped by biology, history, and context. That explanation is usually good enough to trust, and it is always open to revision. Sometimes perception does something unexpected. A straight line appears bent. Two identical sounds feel different in loudness. A steady touch fades until it seems to disappear. These moments are often called illusions, and they're usually treated as curiosities, little tricks that briefly interrupt an otherwise reliable system. But from a scientific perspective, illusions are not mistakes, they are demonstrations. An illusion shows how perception normally works by revealing what happens when its assumptions are pushed in unusual ways. Rather than exposing flaws, illusions expose rules. They show the shortcuts, expectations, and internal models that the brain relies on every moment, usually without drawing attention to itself. Consider visual illusions first, because vision is the sense most people trust the most. One well-known example is the Müller-Lyer illusion, first studied in the 19th century, where two lines of equal length appear different because of the arrow-like shapes attached to their ends. The physical measurement is the same, yet experience insists otherwise. This happens because the brain interprets the shapes as depth cues, applying assumptions about three-dimensional space to a flat image. The illusion is not random, it follows a rule. When the visual system encounters certain angles and configurations, it interprets them as signs of distance and perspective. These assumptions usually help make sense of the world. In this case, they are simply misapplied. The illusion reveals the interpretive process that normally operates invisibly. Another classic example is the checker shadow illusion studied by Edward Adelson, where two squares with identical brightness appear dramatically different because one seems to lie in shadow. The brain automatically compensates for lighting conditions, adjusting perceived brightness based on context. This adjustment usually helps objects appear stable under changing illumination. In the illusion, the compensation becomes visible. Auditory illusions work in similar ways. The McGurk effect, first described by Harry McGurk and John MacDonald in the 1970s, shows how visual information can alter what is heard. When the sound of one syllable is paired with the visual movement of another, the brain often perceives a third sound entirely. Hearing is not just about sound waves. It is about combining multiple sources of information to infer meaning. Again, the illusion follows rules. The brain assumes that visual and auditory cues usually come from the same source. When they conflict, it seeks a compromise that best fits past experience. The result feels real, even though it does not correspond directly to the physical stimulus. Touch provides its own demonstrations. The rubber hand illusion shows how easily the sense of body ownership can be altered. When a fake hand is stroked in synchrony with a hidden real hand, many people begin to feel as though the fake hand belongs to them. The brain integrates visual and tactile signals to maintain a coherent body map. When those signals align in time and space, ownership is inferred. This illusion reveals that the feeling of having a body is not a fixed given. It is an active construction based on correlated information. The brain asks what configuration best explains the sensory input, and it commits to that explanation. These examples share an important feature. They are systematic. The same conditions produce the same effects across individuals. This regularity is why illusions are so valuable in psychology and neuroscience. They allow researchers to infer the underlying mechanisms of perception by observing when and how interpretation changes. Historically, illusions played a key role in shifting scientific understanding away from naive realism. They showed that perception does not simply reflect the world, it interprets it. Figures such as Hermann von Helmholtz used illusions to argue that perception involves unconscious inference. Modern researchers continue this tradition, using carefully designed stimuli to probe predictive processes in the brain. Illusions also highlight the role of expectation. In many cases, the brain chooses the interpretation that best fits prior experience, even when that interpretation conflicts with immediate sensory data. This is not a flaw. It is a consequence of predictive processing. The brain is optimized to handle typical conditions, not artificial edge cases. This is why illusions often feel stable rather than confusing. Once an interpretation is selected, it tends to persist. The brain resists abandoning a prediction unless the error becomes too large to ignore. This stability is what makes the illusion convincing. Experience does not flicker between alternatives, it settles. Gentle humor fits naturally here. The brain can be thought of as extremely confident about its guesses. Most of the time, that confidence is well-deserved. Occasionally, it leads to charming mistakes that reveal how the guessing works. Crucially, illusions do not imply that perception is unreliable in everyday life. On the contrary, they demonstrate how reliable it usually is. The same assumptions that produce illusions in laboratory conditions allow smooth interaction with the real world. Depth cues help navigate space. Brightness constancy stabilizes vision. Multisensory integration supports communication. Predictive processing provides a unifying explanation. The brain continuously predicts what it is likely to encounter. Sensory input is used to update those predictions. Illusions arise when predictions dominate or when input is ambiguous. They are moments where the balance between expectation and evidence becomes visible. This reinforces an important point. Perception is lawful. It follows principles. It is constrained by biology, physics, and learning. Even when it diverges from physical measurement, it does so in consistent, explainable ways. There is nothing arbitrary about an illusion. Understanding this helps soften the idea that perception being indirect is unsettling. The rules that guide interpretation are the same rules that make experience stable and useful. Illusions simply expose the machinery by exaggerating its effects. There's also an important emotional aspect. Illusions remind us that certainty in experience does not require completeness. The world can feel solid and dependable even when it's being actively constructed. Confidence in perception comes from consistency, not from direct access to reality in its entirety. By studying illusions, scientists gain insight into how the brain solves the problem of perception. How does it create a coherent world from limited data? How does it balance expectation and evidence? How does it remain flexible without becoming unstable? Illusions answer these questions not by breaking the system, but by revealing how it works when stretched. They show that perception is not a passive window, but an active, rule-governed process. They make visible the predictive nature of experience. The solid world of daily life remains intact. Chairs still support weight. Sounds still carry meaning. Illusions do not undermine reality. They illuminate how reality is experienced. They show that the brain's best guesses are usually right, and when they are not, they fail in informative ways. Perception follows rules. Those rules are not hidden. They're quietly at work all the time. Illusions simply allow them to be seen. The world behaves very differently depending on how closely it is examined. At the scale of everyday life, objects feel solid and stable. A table resists pressure. A wall blocks movement. A dropped object falls downward at a steady rate. These behaviors feel obvious and intuitive, so familiar that they rarely invite explanation. Reality at this scale seems built from solid pieces that persist through time. This is the scale human intuition evolved to handle. Bodies are large compared to atoms. Movements are slow compared to the speed of light. Forces average out smoothly. Under these conditions, the physical world behaves in ways that match experience closely enough that prediction feels effortless. Cause and effect line up. Objects occupy definite positions. Matter appears continuous. But this picture changes when attention moves away from the human scale. If the structure of matter is examined more closely, solidity begins to dissolve into something stranger. Atoms, once imagined as tiny hard spheres, turn out to be mostly empty space. Their mass is concentrated in a nucleus thousands of times smaller than the atom itself, surrounded by electrons that do not orbit like planets, but exist as spread-out patterns of probability. This understanding emerged gradually at the beginning of the 20th century. In 1900, Max Planck introduced the idea that energy comes in discrete amounts, now called quanta, while studying how objects emit radiation when heated. This marked the beginning of quantum physics, a framework that would challenge classical intuition at its foundations. As experiments probed smaller scales, familiar assumptions began to fail. Light, long understood as a wave, sometimes behaved like a particle. Electrons, thought of as particles, sometimes produced interference patterns characteristic of waves. The distinction between particle and wave became blurred. Objects no longer had simple identities. Niels Bohr played a central role in shaping early interpretations of these findings. His model of the atom showed that electrons occupy discrete energy levels rather than continuous orbits. More importantly, he emphasized that classical descriptions break down at atomic scales. Concepts like position and trajectory, so useful at everyday scales, lose their clear meaning. This breakdown is not a failure of physics. It reflects a change in the structure of reality at different scales. The rules that govern large collections of atoms do not apply cleanly to individual particles. At small scales, probability replaces certainty. Outcomes are described in terms of likelihood rather than definite prediction. This probabilistic nature does not mean that anything can happen. quantum physics is highly precise in what it predicts. It can calculate probabilities with extraordinary accuracy. What changes is the kind of prediction being made. Instead of asking exactly what will happen, the theory asks what is likely to happen and how often. Everyday intuition struggles here because it relies on direct experience. Humans do not interact with individual electrons. There is no sensory system tuned to quantum behavior. The brain evolved to predict falling objects, not probability distributions. As a result, attempts to imagine quantum phenomena often borrow misleading metaphors from the macroscopic world. For example, it is tempting to picture an electron as a tiny ball moving through space. In reality, what exists is a quantum state, a mathematical description of possible outcomes. The electron does not have a precise position until it interacts with something else. Before that interaction, only probabilities can be assigned. This does not mean that reality becomes vague or subjective. Quantum behavior follows strict rules. Experiments performed in laboratories around the world produce consistent results. The same patterns appear again and again. What changes is the relationship between measurement and outcome. As scale increases again, moving from atoms to large collections of particles, familiar behavior re-emerges. Billions of atoms acting together average out quantum uncertainty. Probabilities converge into stable patterns. Objects regain definite shapes and positions. This transition is known as emergence, where simple underlying rules produce complex, stable behavior at larger scales. A useful comparison is weather. Individual air molecules move unpredictably, colliding in chaotic ways. Yet large-scale weather patterns follow recognizable structures. Temperature gradients drive winds. Pressure systems form and persist. Predictability emerges from complexity, even though the underlying components behave irregularly. Solidity itself is an emergent property. The resistance felt when touching a surface arises from electromagnetic forces between atoms, not from physical contact in the everyday sense. Atoms do not touch in the way intuition suggests. Their electron clouds repel one another. The sensation of firmness comes from force, not from matter pressing together. At the scale of everyday experience, these details do not matter. The chair supports weight regardless of how its atoms behave, but understanding that solidity emerges from interactions rather than substance helps clarify why intuition fails at smaller scales. What feels fundamental is often the result of averaging. Time behaves similarly. At human scales, it flows smoothly forward. At microscopic scales, physical laws often work equally well forward and backward in time. Irreversibility emerges statistically, not fundamentally. This is why thermodynamics becomes important when many particles are involved. Reality then does not have a single character. It changes with scale. What appears solid at one level becomes probabilistic at another. What feels continuous emerges from discrete interactions. This does not imply contradiction. It reflects layered descriptions, each valid within its domain. Understanding this helps place perception in context. The brain evolved to model reality at the scale that matters for survival. It does not represent atomic probability clouds or quantum states. It represents tables, faces, edges, and motion. These representations are accurate where they need to be accurate. The earlier discussion of perception as prediction fits naturally here. Just as the brain constructs experience from limited information, science constructs models of reality appropriate to different scales. Neither approach is wrong. Each is tuned to a specific level of description. There's a quiet elegance in this arrangement. Reality supports multiple layers of explanation without collapsing into inconsistency. Classical physics describes everyday motion. Quantum physics describes microscopic behavior. Each theory works where it applies. Confusion arises only when intuition from one scale is forced onto another. Gentle humor is sometimes unavoidable here. Expecting atoms to behave like tiny billiard balls is a bit like expecting individual ants to follow traffic laws. The rules change with context. This shift in scale marks an important transition. Until now, attention has focused on how the brain constructs experience. Here, attention turns outward, toward the structure of the physical world itself. The indirect nature of perception is mirrored by the layered nature of reality. What is experienced directly is a simplified emergent surface. Beneath it lies a deeper structure that does not resemble everyday intuition. That structure is not hidden by deception. It is hidden by scale. Reality is not less real at smaller scales. It is simply different. Understanding this difference allows questions about perception and physics to meet without contradiction. The world feels solid because at the scale of human life it effectively is. At other scales, other rules apply. This recognition forms a bridge. On one side lies the brain, predicting and interpreting. On the other lies the physical world, structured in layers. Between them sits experience, shaped by both. Observation sounds passive. In everyday language, to observe means to look, to watch, to notice what is already there. A bird is observed on a branch. A cloud is observed drifting overhead. The world appears to unfold on its own, while the observer simply takes it in. This intuition works well for ordinary experience, but in science, observation means something more specific. In physics, observation is not about awareness, it is about interaction. To observe a system is to let it interact with something else in a controlled way. A detector absorbs energy. A particle collides with an instrument. A measuring device responds to a physical process. Information is exchanged, and that exchange leaves a trace. This distinction matters because interaction is never neutral. Any interaction capable of revealing information also changes the system being observed, at least slightly. At everyday scales, this change is so small that it can be ignored. Measuring the length of a table does not meaningfully alter the table. Listening to a sound does not disrupt its source in any noticeable way. The effects exist, but they are drowned out by scale. At very small scales, this balance shifts. When dealing with atoms and subatomic particles, the act of measurement can no longer be separated from the system itself. To detect an electron, something must interact with it. That interaction transfers energy and momentum. The system before measurement and the system after measurement are not identical. This is not because of human attention or consciousness. It is because of physics. This idea is often misunderstood, so it helps to be precise. Measurement does not create reality. It does not summon outcomes from nothing. What measurement does is constrain possibilities. Before interaction, a system may be described by a range of possible outcomes. After interaction, one of those possibilities has been realized. In quantum physics, this shift is described using probability. Before measurement, a system is described by a quantum state that assigns probabilities to different outcomes. After measurement, a specific result is recorded. The mathematics handles this transition with extraordinary accuracy. The challenge lies not in predicting results, but in interpreting what the process means. One of the earliest thinkers to confront this issue was Niels Bohr. He emphasized that classical concepts like position and momentum cannot always be applied simultaneously at quantum scales. Measurement forces a choice about what is being asked. An experiment designed to measure position will produce precise position information, but at the cost of information about momentum. This is not a limitation of instruments. It reflects how nature behaves. This idea is closely related to the uncertainty principle, introduced by Werner Heisenberg, which states that certain pairs of properties cannot both be known with arbitrary precision at the same time. The principle is often described loosely, but its core message is simple. The structure of reality itself limits what can be simultaneously defined. Importantly, uncertainty here does not mean ignorance. It means that reality at small scales does not possess all classical properties at once. Measurement does not merely reveal values that were already there. It participates in defining which properties become definite. This does not imply that measurement depends on human observers. Instruments do not need to be watched to function. A detector at a particle accelerator records events whether or not anyone is present. The interaction happens regardless of awareness. Consciousness plays no role in triggering outcomes. This point has been tested repeatedly in experiments conducted at major research institutions such as CERN and national laboratories around the world. Particle collisions, decay events, and quantum interactions are recorded automatically by machines. The data accumulates quietly, long before any human looks at it. What matters is interaction, not attention. Different interpretations of quantum mechanics attempt to explain what measurement means at a deeper level. Some emphasize wave function collapse, where probabilities reduce to a single outcome. Others emphasize decoherence, where interactions with the environment rapidly suppress interference between possibilities, making one outcome effectively stable. Still others propose many worlds or relational descriptions. What they share is a recognition that measurement is a physical process embedded in the same reality it probes. No interpretation suggests that human thought controls particles. The mystery lies in how physical systems transition from multiple possibilities to single outcomes, not in who is watching. Decoherence is particularly useful for grounding intuition. When a quantum system interacts with its environment, information about its state becomes spread across many degrees of freedom. Interference effects disappear rapidly. At that point, the system behaves classically for all practical purposes. Outcomes become stable and repeatable. This explains why everyday objects do not appear to exist in multiple states at once. They are constantly interacting with their surroundings. Air molecules, photons and thermal vibrations entangle with them continuously. Quantum ambiguity is washed out long before it can be noticed. Measurement, then, is not a special magical act. It is an extension of interaction. At small scales, interactions matter more because they are comparable in size to the systems involved. At large scales, interactions average out, and measurement becomes effectively passive. This mirrors the earlier discussion of perception. The brain does not observe the world by standing apart from it. It interacts with it through sensory receptors. Photons strike the retina. Sound waves move the inner ear. Mechanical pressure deforms skin. Each of these interactions changes both the body and the environment, even if the changes are tiny. The brain then interprets these interactions, constructing experience from the traces they leave behind. In this sense, perception and measurement share a deep structural similarity. Both rely on interaction. Both involve inference. Both trade completeness for stability. A measuring instrument can be thought of as a simplified sensory system. It is designed to respond to specific physical quantities. A thermometer responds to temperature. A photodetector responds to light. Each instrument filters reality, highlighting certain features while ignoring others. Just as perception does not capture everything, measurement does not either. Every experiment selects which questions can be asked. There is no view from nowhere. There are only interactions arranged in particular ways. This does not weaken science. It strengthens it. By carefully designing interactions, scientists can probe specific aspects of reality with remarkable precision. The limitations are understood, quantified, and accounted for. Measurement uncertainty is not a philosophical problem. It is a practical parameter. There is a quiet humility in this approach. Physics does not claim to reveal reality in its entirety. It claims to model how systems behave under defined interactions. The success of this approach is evident in technology, medicine, and engineering, all of which depend on reliable measurement at many scales. Gentle humour fits here as well. The universe is not shy. It does not hide information out of spite. It simply responds to how it is touched. Ask one question, and it answers that question. Ask a different one, and a different answer appears. The responsibility lies with the question, not the universe. Understanding observation as interaction helps dissolve a common confusion. Reality does not wait to be seen. It does not flicker into existence when noticed. It evolves continuously according to physical laws. Measurement is one way of participating in that evolution, not a trigger that brings it into being. This perspective keeps the discussion grounded. It avoids exaggeration while preserving wonder. At small scales, reality behaves in ways that challenge intuition. At large scales, those behaviors average out into the solid world of experience. Measurement sits at the boundary, linking abstract description to concrete outcome. The parallel with perception remains strong. Both brain and instrument operate by sampling, filtering, and inferring. Both rely on interaction rather than passive reception. Both reveal a world that is stable, structured, and responsive, even when it refuses to be fully transparent. Observation, understood properly, does not undermine reality. It clarifies how reality is known. Reality feels stable because time behaves predictably. Events appear in a reliable order. Causes come before effects. The past feels fixed. The future feels open, and the present feels like a moving boundary between the two. Objects persist from one moment to the next. Identity survives change. A chair remains the same chair even as light shifts across its surface and dust slowly gathers. This continuity is so familiar that it rarely invites attention. Time seems to flow naturally, carrying the world along with it. Experience unfolds as a smooth sequence, moment following moment, without interruption. Stability emerges not because nothing changes, but because change itself follows regular patterns. This intuitive sense of time underpins nearly every aspect of perception. Without it, experience would fragment. Sounds would not form melodies. Motion would not trace paths. Memory would have no order. The world would lose coherence. Time binds experience together. Yet beneath this familiarity lies a subtle scientific puzzle. In fundamental physics, most basic laws do not distinguish between past and future. The equations that describe motion, electromagnetism, and even quantum processes often work equally well forward or backward in time. Nothing in those laws, by themselves, demands a preferred direction, and yet experience is unmistakably directional. Glass shatters but does not reassemble. Smoke disperses but does not gather itself back into a flame. People grow older, not younger. The arrow of time feels obvious, even inevitable. The key to this asymmetry lies in thermodynamics, the branch of physics that deals with heat, energy, and large collections of particles. Central to thermodynamics is the concept of entropy, a measure often described as disorder, but more precisely understood as the number of microscopic arrangements consistent with a macroscopic state. Ludwig Boltzmann, working in the late 19th century, provided the statistical foundation for entropy. He showed that systems naturally evolve from less probable states to more probable ones. There are many more ways for particles to be disordered than ordered. As a result, systems tend to move towards states of higher entropy over time. This statistical tendency gives time its direction. When a cup falls and breaks, the shards can be arranged in countless ways across the floor. The intact cup represents a highly specific, unlikely configuration. The broken pieces represent many more possible configurations. Moving from order to disorder is overwhelmingly more probable than the reverse. The laws of motion allow both. Statistics strongly favor one. This explains why irreversible change dominates everyday experience. It is not that the past cannot return in principle, it is that it almost never will. The numbers involved are staggering. For macroscopic systems containing trillions upon trillions of particles, the probability of spontaneous reversal is effectively zero. Time's arrow, then, emerges from scale. At microscopic levels, reversibility remains possible. At macroscopic levels, probability takes over. Stability arises not from stillness, but from overwhelming statistical regularity. This statistical view of time fits neatly with earlier ideas about emergence. Just as solidity emerges from atomic interactions, temporal direction emerges from large numbers. The flow of time is not imposed from outside. It arises from how matter behaves when many components interact. Yet the experience of time involves more than physics alone. The brain plays a crucial role in shaping how time is felt. Perception does not register the present as a single instant. Instead, it integrates information over short intervals, smoothing change into continuity. Sounds are grouped into syllables, movements are stitched into trajectories, events are ordered into sequences. Memory anchors this process. The past feels real because it is remembered. The future feels uncertain because it is predicted rather than recalled. This asymmetry between memory and anticipation reinforces the direction of time in experience. The brain stores traces of what has already occurred. It does not store traces of what has not. Neuroscience shows that temporal perception relies on networks that integrate sensory input, expectation, and memory. There is no single clock in the brain. Instead, timing emerges from distributed processes that track change, rhythm, and duration. This allows time to feel flexible. Moments can stretch or compress depending on attention, emotion, and context. Despite this flexibility, the underlying order remains intact. Events still follow one another, causes still precede effects. Even when time feels slow or fast, it still moves forward. This alignment between physical time and experienced time is not accidental. The brain evolved within a world governed by thermodynamic regularities. Memory formation depends on irreversible physical processes. Neural activity leaves traces. Learning changes synapses. These changes do not spontaneously undo themselves. In this sense, the brain is itself a thermodynamic system. It records the past by increasing entropy locally, while exporting disorder to the environment. Memory is not free. It is paid for with energy. This grounding keeps temporal experience tethered to physical reality. The flow of time is not an illusion created by the mind alone. It is a reflection of how matter behaves at scale, mirrored in neural processes that track change and store history. Yet time remains scientifically subtle. While thermodynamics explains why time has a direction, it does not fully explain why the universe began in a low entropy state in the first place. This initial condition is essential. Without it, there would be no arrow of time to follow. Cosmology grapples with this question, exploring why the early universe was so ordered and how that order shaped everything that followed. This uncertainty does not undermine what is known. It marks the boundary between established understanding and open questions. Physics can describe how time behaves and why it flows the way it does within the universe we observe. It does not yet explain why those conditions existed at the beginning. For everyday experience, this distinction rarely matters. The arrow of time is robust. Stability emerges because change follows patterns. Objects persist because entropy increases slowly at familiar scales. Life is possible because the universe allows gradients, differences, and flows. There is a gentle reassurance here. Stability does not require permanence, it requires reliable change. The world holds together because it changes in predictable ways. Time provides the scaffold for that reliability. It orders events, supports memory, and allows learning. It gives meaning to cause and effect. Without it, reality would lose coherence. Connecting this back to perception completes a larger picture. The brain predicts, interprets, and remembers within a world that changes irreversibly. Perception depends on continuity. Memory depends on direction. Stability emerges from processes that are anything but static. Reality feels solid not because it is frozen, but because it unfolds lawfully through time. Change does not threaten stability, it creates it. Time, then, is not merely a backdrop. It is an active participant in shaping experience and physical structure alike. It anchors perception, supports memory, and allows the world to persist as something recognizable from one moment to the next. The flow of time feels obvious because it is everywhere. Its deeper nature remains subtle because it emerges from statistics, scale, and history, rather than simple mechanisms, yet its effects are unmistakable. Reality holds together because time moves forward, quietly and reliably, carrying both matter and experience along with it. At first glance, space seems like an empty stage. Objects appear to sit within it, separated by distances, occupying positions as though space were a passive container, holding everything in place. A chair rests on the floor. A wall stands a few steps away. Between them, there appears to be nothing at all. Space feels like absence, a gap between things. Modern physics tells a different story. Rather than being an empty backdrop, space is active, it is structured. It is filled with physical quantities that extend everywhere, even where no objects seem to be present. These quantities are known as fields, and they form the foundation of how contemporary science describes reality. A field is a physical entity that assigns a value to every point in space and time. Temperature across a room is a familiar example. At every location there is a temperature, even if nothing is placed there. Wind speed across a landscape behaves similarly. The wind exists not just where leaves move, but throughout the air itself. Electromagnetic fields work in much the same way, though they are invisible. At every point in space there can be an electric field and a magnetic field, influencing charged particles and currents. These fields are not carried by objects, they exist in space itself. James Clerk Maxwell, working in the mid-19th century, unified electricity and magnetism into a single framework. His equations showed that electric and magnetic fields are deeply linked and that changes in these fields propagate through space as waves. Light itself turned out to be an electromagnetic wave, travelling through space without needing a medium. This realization reshaped physics. Light was no longer something that moved through space. It was something that happened in space. Space was no longer empty. It was active and responsive. As physics advanced into the 20th century, the field concept expanded further. Quantum field theory, the framework underlying modern particle physics, treats particles not as fundamental objects, but as excitations of underlying fields. An electron is not a tiny solid bead. It is a localized disturbance in the electron field. A photon is an excitation of the electromagnetic field. From this perspective, what appears to be solid matter is a pattern of interacting fields. The distinction between object and space becomes blurred. Space is not just where things are, it is part of what things are. This helps explain a puzzle that has appeared repeatedly. If atoms are mostly empty space, why does matter feel solid? Why does a table resist a hand rather than letting it pass through? The answer lies in interactions, not substance. When a hand presses against a table, the electrons in the atoms of the hand encounter the electrons in the atoms of the table. These electrons interact through the electromagnetic field. Like charges repel. The resistance felt is the result of this repulsion, mediated by fields, not by atoms physically touching in the everyday sense. Solidity emerges from force, not from filled space. It is an effect of interactions that become apparent at large scales. The feeling of firmness is a macroscopic experience arising from countless microscopic field interactions acting together. This understanding fits naturally with earlier discussions of scale and measurement. At small scales, particles behave according to quantum rules. At larger scales, the combined effect of many interactions produces stable structures. Fields provide the continuity between these levels. Fields also explain why forces act across apparent emptiness. Gravity influences objects across vast distances. Electromagnetism binds atoms together. These influences do not require contact. They are properties of space structured by fields. Even gravity, described by Albert Einstein's general theory of relativity, is not a force in the traditional sense. It arises from the curvature of space-time itself, shaped by mass and energy. Objects follow paths determined by this curvature. Space and time are not passive, they participate. This view can feel counterintuitive because it departs from everyday experience. The brain evolved to represent objects, not fields. A chair is easier to think about than an electromagnetic interaction pattern. The brain compresses complexity into stable entities that can be named and manipulated. Science, however, is free to unpack that compression. When it does, the solid world dissolves into relationships, interactions, and structures extended across space. There is a quiet beauty here. Reality is not built from tiny bricks stacked together. It is woven from continuous influences that overlap and combine. Objects emerge where fields interact in stable ways. Space itself is part of the structure. This also clarifies why measurement and interaction matter so much. Measuring a system means coupling it to a device through fields. Energy flows. Information is exchanged. Nothing happens in isolation. Even a detector sitting quietly in space is immersed in fields that allow it to function. Quantum field theory makes this explicit. The vacuum, often imagined as empty, is filled with fluctuating fields. These fluctuations have measurable effects, such as shift in atomic energy levels and forces between closely spaced surfaces. Emptiness is not nothing. It is a dynamic baseline. At human scales, these effects are subtle. The world feels calm and still. At microscopic scales, activity is constant. Fields vibrate. Interactions occur. Stability emerges from balance, not from stillness. This layered understanding helps reconcile intuition with physics. The chair feels solid because, at the scale of hands and bodies, electromagnetic interactions are strong and reliable. At the scale of atoms, those same interactions look probabilistic and spread out. At the scale of fields, they are continuous and everywhere. None of these descriptions contradict one another. They describe the same reality from different perspectives. Objects are useful summaries. Fields are deeper explanations. There is gentle humour in realizing that what feels like solid matter is mostly force saying no. Space is not empty. It is busy. It just happens to be busy in ways that are well behaved at everyday scales. Understanding reality as structured by fields rather than objects does not make the world less real. It makes it more coherent. It shows how stability emerges from interaction, how space participates in physical processes, and how solidity arises without requiring substance in the traditional sense. The journey from perception to physics now reaches into the fabric of space itself. The brain constructs experience by predicting patterns. Instruments measure by interacting through fields. Matter holds together because fields organize energy into stable forms. Space is not the absence between things. It is the medium through which reality takes shape. Information is often treated as something abstract. It sounds like an idea rather than a physical thing, a message, a description, a pattern of meaning carried by words or symbols. In everyday language, information feels detached from matter, floating freely between minds and machines. Modern science takes a different view. In physics, information is physical. This statement is not a metaphor. It is a principle grounded in experiment and theory. Information can be measured. It can be stored. It can be transferred. And crucially, it is constrained by the laws of nature. It is tied to energy, matter, and time. The formal study of information began in the mid-20th century with the work of Claude Shannon. While working at Bell Laboratories in the 1940s, Shannon developed a mathematical framework for understanding communication. His information theory did not concern meaning. It concerned uncertainty. Information, in this sense, measures how much uncertainty is reduced when a message is received. If a message is entirely predictable, it carries little information. If it is surprising, it carries more. This idea can be quantified. Information becomes a measurable quantity, expressed in units that reflect how many distinct possibilities are being distinguished. What made Shannon's work powerful was its generality. It applied equally well to telephone signals, written text, digital data, and noise. Information was no longer subjective. It became something that could be counted, compressed, and transmitted efficiently. This abstract framework soon revealed deep physical connections. In thermodynamics, entropy had already been defined as a measure of how many microscopic arrangements correspond to a macroscopic state. This is strikingly similar to Shannon's definition of information. Both involve counting possibilities. Both quantify uncertainty. The link is not accidental. When a physical system has high entropy, it contains less usable information about its precise microscopic state. When entropy is low, more information is available. This relationship led physicists to recognize that information and entropy are closely related aspects of the same underlying reality. One of the most important insights to emerge from this connection is that erasing information has a physical cost. This was formalized by Rolf Landauer in the 1960s. Landauer showed that deleting a bit of information requires a minimum amount of energy to be dissipated as heat. Information processing is not free, it is constrained by thermodynamics. This principle applies to all computing systems, from silicon chips to biological brains. Every time a bit is erased, entropy increases somewhere. This grounds information firmly in the physical world. It is not merely abstract. It is something that must be carried by physical states. Modern computing makes this visible. Data is stored in physical media. Electric charges, magnetic domains, or quantum states represent information. Transmitting information requires energy. Processing information generates heat. Limits on computation are limits imposed by physics itself. Physics goes further still. In fundamental theories, information increasingly appears as a central concept rather than a secondary one. Black hole physics provides a striking example. Research into black holes revealed that they possess entropy proportional to the area of their event horizons. This suggests that information about everything that falls into a black hole is somehow encoded on its boundary rather than lost. This insight led to the idea that information is conserved in physical processes, even in extreme conditions. While the details remain an active area of research, the implication is profound. Information is not destroyed, it is transformed and redistributed. Quantum physics reinforces this view. The state of a quantum system encodes information about probabilities of outcomes. Measurement extracts information by interacting with the system. Entanglement links information across space in ways that defy classical intuition, while still respecting physical constraints. In this context, physical laws can be reframed as rules governing how information flows and changes. Dynamics describe how information evolves over time. Conservation laws constrain what information can be created or destroyed. Fields and interactions become channels through which information moves. This perspective does not replace traditional physics, it complements it. Energy, momentum, and charge remain fundamental. Information provides a different lens through which to understand how those quantities are organized and constrained. This brings the discussion back to perception. The brain is an information processing system embedded in a physical world. Sensory receptors gather information from the environment. Neural circuits transform it. Memory stores it. Prediction uses it to anticipate future states. All of this relies on physical processes governed by thermodynamics and energy constraints. Perception, in this light, is the extraction of information from interaction. Photons striking the retina carry information about surfaces and light sources. Sound waves carry information about vibrations and events. The brain does not receive the world itself, it receives information about the world. Predictive processing fits naturally here. The brain minimizes surprise by reducing uncertainty. It uses prior information to interpret incoming signals. It updates internal models to better predict future input. In effect, it manages information efficiently under physical constraints. This efficiency is not optional. The brain consumes energy. Neural activity generates heat. There are limits to how much information can be processed at once. Evolution shaped nervous systems to extract the most relevant information with the least cost. There is a subtle but important implication here. Reality, as experienced, is shaped by information flow. What is perceived depends on what information is available, how it is filtered, and how it is interpreted. The structure of experience reflects the structure of information exchange. This does not mean that reality reduces to information in a simplistic way. matter and energy remain fundamental, but information describes how those elements are arranged, correlated, and constrained. It captures patterns rather than substances. A book is paper and ink. Its information lies in the arrangement of marks. A brain is tissue and electricity. Its information lies in patterns of activity. The physical substrate matters, but the organization carries meaning. There is gentle humor in noticing that the universe is constantly processing information without caring whether anyone calls it that. Stars evolve by redistributing energy and information. Molecules interact by exchanging information about states. Life emerges by exploiting information gradients. From this perspective, the question of reality shifts slightly. Reality is not just what exists. It is how what exists is structured, constrained, and connected. Information provides a language for describing those connections. This perspective also reinforces earlier themes. Perception is indirect because it relies on information rather than direct access. Prediction is necessary because information is incomplete. Measurement matters because it extracts information through interaction. Time matters because information accumulates irreversibly. Information ties these threads together without dissolving reality into abstraction. It remains grounded in physics. It obeys limits. It costs energy. It leaves traces. Understanding information as physical helps explain why experience feels stable despite complexity. The brain does not need complete information. It needs sufficient information to act reliably. Reality supplies that information through lawful processes. The world then can be seen as a vast network of information flows shaped by physical laws. Experience is a localized pattern within that network. Prediction, memory, and perception are strategies for navigating it. Information does not replace reality. It describes how reality communicates with itself. The brain is not separate from the world it tries to understand. It is made of the same matter, governed by the same physical laws, and embedded within the same environment it attempts to model. Neurons obey chemistry. Electrical signals follow physics. Energy is consumed, heat is produced, and structure is maintained only through constant interaction with the surrounding world. This simple fact carries an important consequence. The brain does not stand outside reality and observe it from a distance. It is inside reality, shaped by it, acting within it, and constrained by it. Any picture the brain forms of the world is therefore created from within the system it describes. This embeddedness creates feedback loops. An organism acts on its environment. The environment responds. Sensory systems register the consequences of those actions. The brain updates its internal model. That updated model then guides future actions. Perception, prediction, and behavior form a continuous cycle rather than a linear chain. A simple example is movement. When a body reaches for an object, the brain predicts how the arm will move and what sensations will follow. Muscles contract. The arm moves. Sensory feedback confirms or corrects the prediction. Adjustments are made in real time. The model and the world shape each other moment by moment. This loop operates at every scale of behavior. Walking, speaking, breathing, and even maintaining posture all rely on continuous interaction between internal expectations and external feedback. The brain is not passively receiving information. It is actively testing its predictions through action. Research in embodied cognition emphasizes this point. Rather than treating the brain as an isolated information processor, embodied cognition views cognition as arising from the interaction between brain, body, and environment. Thought is not confined to neural activity alone. It is distributed across perception, movement, and context. Experiments in psychology and neuroscience have shown that bodily states influence perception and judgment. The weight of an object can affect estimates of distance. Posture can influence emotion. Action possibilities shape what is noticed. These findings highlight that cognition is grounded in physical interaction, not abstract computation alone. This grounding limits what the brain can know. Because the brain is part of the system it models, it cannot obtain a complete description of that system from the outside. It must rely on partial information gathered through interaction. There is no direct access to the world as it is in itself. There is only access to the world as it responds to probes. This is not a special limitation of biological systems. It applies to any system attempting to model itself or its environment from within. Self-modeling systems face inherent constraints. They cannot include every detail of themselves in their own models without infinite regress. Some simplification is unavoidable. The brain deals with this by building models that are useful rather than complete. It focuses on regularities, patterns, and relationships that matter for survival and action. Details that do not affect outcomes are ignored. This selective modeling allows efficient operation even though it guarantees incompleteness. This is another reason perception feels indirect. The brain is not attempting to reconstruct reality in full detail. It is attempting to maintain a stable relationship with the environment. Its models are pragmatic tools rather than exhaustive representations. Feedback loops reinforce this pragmatism. When a prediction leads to successful action, it is reinforced. When it fails, it is adjusted. Over time, the brain learns which patterns are reliable. These learned regularities become the structure of experience itself. This learning process is deeply physical. Synapses change strength. Neural circuits reorganize. Energy is consumed. Memory leaves lasting traces. The brain carries its history with it, shaping how new information is interpreted. Because of this history, perception is never neutral. What is seen, heard, or felt depends on what has been learned before. Experience is filtered through accumulated interactions. The brain's model of the world is always a work in progress, shaped by past feedback. This does not imply that reality is subjective or arbitrary. The environment provides strong constraints. A cliff does not become safe through belief. A flame does not stop burning because it is inconvenient. Physical laws push back against mistaken models. Organisms that fail to align their predictions with reality do not persist. The result is a tight coupling between brain and world. The brain adapts to the structure of reality because it must. Reality shapes cognition as much as cognition shapes experience. There is a subtle consequence here. Because the brain's models are shaped by interaction, they reflect the world at the scale and resolution relevant to the organism. Humans model a world of objects, surfaces, and social agents. Bats model a world of echoes. Bacteria model chemical gradients. Each organism lives in a different informational slice of the same physical reality. This diversity does not fragment reality. It reveals its richness. Different systems extract different information depending on their structure and needs. The underlying world remains the same. The models vary. This brings the theme of indirect access into sharper focus. No organism experiences reality directly. Each experiences a mediated version shaped by sensory capabilities, bodily structure, and evolutionary history. The brain's model is always an interface, never a full mirror. Yet this interface is remarkably effective. It allows planning, cooperation, technology, and reflection. It supports science itself. which is an extension of these modelling processes using instruments and shared methods. There is gentle humour in realising that the brain, while trying to understand reality, is also one of the things reality is doing. The attempt to comprehend the universe is itself a physical process unfolding within the universe. Thought is not outside nature, it is part of it. This recursive situation does not lead to paradox, it leads to humility. The brain's models are powerful, but they are not final. They can be improved, refined, and sometimes replaced. They remain anchored to interaction rather than absolute access. Understanding the brain as embedded clarifies why certainty has limits. Some questions cannot be answered from within a system without additional assumptions. Some perspectives are inaccessible. This does not weaken knowledge, it defines its scope. The brain inside the world it models must trade completeness for coherence. It must rely on feedback rather than detached observation. It must build stable approximations rather than perfect copies. This is not a flaw. It is the only way modelling can work from the inside. Reality does not need to be fully captured to be navigated successfully. The brain's task is not to possess the world, but to stay in step with it. Through continuous interaction, prediction, and correction, it does exactly that. Experience, then, is the meeting point of a physical brain and a structured world, each shaping the other in quiet loops of cause and effect. Understanding this deepens the sense that perception is indirect without making it unreliable. The brain does not stand apart from reality. It lives within it, learning its contours one interaction at a time. If perception is indirect, a natural question follows. How can science claim to describe an objective reality at all? After all, every observation is made by a brain. Every measurement is read by an instrument designed and interpreted by humans. Experience varies from person to person. If reality is always filtered through perception, how can any shared picture of the world be trusted? Science answers this question not by denying subjectivity, but by working around it. Rather than relying on any single perspective, science builds knowledge through agreement. It does this by creating methods that allow many observers, using different tools in different places, to arrive at the same results. Objectivity in this sense is not the absence of subjectivity. It is the outcome of disciplined comparison. Replication is central to this process. An experiment is not considered reliable because it convinces one researcher. It is considered reliable because it produces the same outcome when repeated by others under similar conditions. When a result holds across laboratories, cultures, and equipment, it earns credibility. Individual perception becomes less important as patterns emerge. Measurement standards play a crucial role here. Science depends on shared units and definitions that allow results to be compared meaningfully. Length, time, mass, temperature, and electrical charge are defined in precise ways that do not depend on personal experience. Organizations such as the International Bureau of Weights and Measures maintain these standards. They define the second using atomic transitions, the meter using the speed of light, and the kilogram using fixed physical constants. These definitions ensure that a measurement in one country means the same thing in another. This standardization anchors science to physical reality rather than perception. A meter does not stretch or shrink depending on who looks at it. A second does not speed up or slow down based on feeling. Instruments may vary in precision, but the quantities they aim to measure are fixed by convention and physical law. Consensus emerges from this shared framework. When many independent lines of evidence converge, confidence grows. Different methods support the same conclusion. Observations align with predictions, models explain existing data, and successfully anticipate new results. Agreement forms not because of authority, but because of consistency. This process is slow and sometimes messy. Disagreements occur, results are challenged, methods are refined. This is not a weakness. It is the mechanism by which errors are identified and corrected. Science advances by narrowing uncertainty through repeated testing. Subjective experience does not undermine this process because it is not the final authority. Personal impressions are replaced by recorded data. Individual judgment is balanced by peer review. Claims are evaluated based on evidence rather than conviction. Importantly, science does not require that observers perceive the world in exactly the same way. It requires that measurements made under defined conditions produce consistent results. A thermometer does not need to feel temperature. It needs to respond predictably to heat. An instrument does not need awareness. It needs reliability. This distinction matters. A person may feel that a room is warm or cool depending on context, expectation, or physiology. A thermometer reports a numerical value based on physical interaction. That value can be checked against other instruments. Agreement does not depend on sensation, it depends on response. In this way, science externalizes observation. It builds systems that reduce reliance on human perception by embedding measurement in physical processes. Cameras detect light beyond human vision. Radio telescopes detect wavelengths the eye cannot see. Particle detectors record events far too small or fast to experience directly. These instruments extend perception without inheriting its limitations. They still interact with the world physically, but they do so in controlled and repeatable ways. The data they produce can be shared, stored, and reanalyzed independently of the original observer. This collective approach creates stability. Even though individual experience is indirect, the agreement among many observers constrains what can reasonably be claimed. A result that depends on a particular perspective will fail to replicate. A result that reflects an underlying regularity will persist. There is a quiet reassurance in this. Reality does not need to be experienced directly to be known reliably. It needs to behave consistently under interaction. Science relies on that consistency. This also clarifies why acknowledging the limits of perception does not lead to relativism. Recognizing that experience is constructed does not imply that all interpretations are equally valid. The physical world pushes back. Predictions succeed or fail. Models either align with observation or they do not. Scientific objectivity is therefore procedural rather than absolute. It arises from methods designed to minimize bias, reveal error, and converge on stable descriptions. It does not claim perfect access. It claims reliable access. This perspective helps stabilize the broader discussion. The fact that perception is indirect does not dissolve reality into illusion. It explains why tools, methods, and collaboration are necessary. Science is a social extension of individual perception, built to overcome its limitations. There is gentle humor in noting that no single human could ever verify modern physics alone. Knowledge emerges from networks of cooperation, not solitary insight. Reality, in this sense, is confirmed collectively. The success of this approach is evident everywhere. Technologies function, medicines work, predictions hold, satellites orbit accurately, clocks synchronize across continents. These achievements depend on shared models that reliably match how the world behaves. Science does not require certainty about ultimate foundations to be effective. It requires consistency, testability, and openness to revision. Its models are provisional, but they are grounded. Objective reality, as science approaches it, is not a philosophical abstraction. It is the set of regularities that remain when subjective differences are averaged out. It is what persists across perspectives. Understanding this provides balance. The exploration of perception, prediction, and interpretation has revealed depth and complexity. This exploration does not end in doubt. It ends in appreciation for the methods that allow knowledge to remain stable despite those complexities. Reality may be indirectly experienced, but it is not negotiable. The world responds in lawful ways. Science listens carefully, compares widely, and adjusts accordingly. This shared listening is what turns individual uncertainty into collective understanding. Physics has been remarkably successful at describing the world, from the motion of planets to the behavior of atoms, from the flow of electricity to the bending of light. Its theories have explained an enormous range of phenomena with extraordinary precision. Predictions made on paper have been confirmed decades later by experiment. Technologies built on abstract equations quietly support daily life. This success can make it tempting to assume that physics is close to complete. It is not. There are places where current theories fall silent, not because reality disappears, but because existing frameworks no longer apply cleanly. These boundaries are not hidden. They are well known, openly discussed, and actively explored. Acknowledging them is not a weakness. It is part of scientific honesty. One of the most significant gaps lies between quantum physics and gravity. Quantum theory describes the behavior of matter and energy at very small scales with astonishing accuracy. General relativity describes gravity and the structure of space-time at very large scales with equal success. Each theory works extremely well within its domain. They do not yet fit together. When gravity becomes strong at very small scales, such as near the center of a black hole or at the earliest moments of the universe, neither framework can be applied with confidence. The mathematics breaks down. Predictions become unreliable. Physics does not yet have a complete theory of quantum gravity. Many approaches exist. String theory, loop quantum gravity, and other frameworks attempt to reconcile these domains. Each offers insights. None has yet been confirmed experimentally. These ideas are studied seriously, but they remain provisional. Cosmology presents its own open questions. Observations show that the universe is expanding. Measurements of distant galaxies reveal that this expansion is accelerating. To explain this behavior, physicists invoke dark energy, a term that labels the observed effect rather than fully explaining its nature. Similarly, dark matter is inferred from gravitational effects on galaxies and clusters, yet its composition remains unknown. These are not minor details. Together, dark matter and dark energy appear to make up the majority of the universe's total content. Ordinary matter, the kind that forms stars, planets, and bodies, is a small fraction of the whole. Physics can describe how these unseen components behave gravitationally, but not what they are. Even time itself presents unanswered questions. Physics can describe how time behaves within known frameworks. It can explain why entropy increases and why change appears irreversible. It cannot yet explain why the universe began in a low entropy state that allowed time to have a direction at all. This initial condition remains an open puzzle at the intersection of cosmology and fundamental physics. Institutions such as CERN exist precisely to probe these boundaries. Particle accelerators collide matter at enormous energies, recreating conditions not seen since the early universe. Detectors record vast amounts of data, searching for deviations from existing theories. Most results confirm what is already known. Occasionally they reveal hints of something new. This slow pace is deliberate. Frontier science advances cautiously. Extraordinary claims require extraordinary evidence. When physics is silent, it resists the urge to fill the gap with confident speculation. This restraint is important. It can be tempting to treat unanswered questions as invitations for sweeping conclusions. To declare that reality is unknowable, illusory, or fundamentally mysterious in some dramatic sense. Science does not do this. It distinguishes carefully between what is known, what is unknown, and what may be knowable in principle. Silence does not imply absence. A lack of explanation does not imply that anything goes. It means that current tools are insufficient, not that reality has stopped obeying rules. There is a difference between uncertainty and confusion. Physics often knows precisely where its understanding ends. It can identify the conditions under which equations fail. It can estimate the scales at which new effects should appear. This is structured ignorance, not vague doubt. For example, quantum field theory predicts phenomena with extraordinary accuracy, sometimes matching experimental results to more than 10 decimal places. At the same time, it signals its own breakdown at extremely high energies. Both statements can be true. Precision and limitation coexist. This intellectual honesty creates space for uncertainty without exaggeration. It allows wonder without distortion. It avoids turning unanswered questions into myths. There's also a practical reason for this restraint. Many questions that once seemed unanswerable eventually yielded to better experiments and deeper theory. The nature of atoms, the source of stellar energy, the structure of the genome, and the age of the universe were once mysteries. Careful work transformed them into established knowledge. This history encourages patience. Silence today does not guarantee silence tomorrow. But it also encourages humility. Not every question may have an answer accessible from within the universe as it is. This returns the discussion to a familiar theme. The brain, embedded in reality, builds models from within. Physics does the same at a collective scale. It constructs descriptions constrained by measurement, interaction, and consistency. When those constraints are insufficient, it stops rather than pretending otherwise. There is something quietly stabilizing about this. Knowing that science does not claim final answers can be reassuring. It shows that knowledge is not brittle. It adapts. It refines itself. It leaves room for revision without collapsing. This approach also protects against unnecessary mystery. The unknown does not automatically imply the unknowable. It simply marks the edge of current understanding. Gentle humor fits here as well. The universe is not promised to explain itself on a human timetable. It reveals patterns when conditions allow. It remains quiet when they do not. Physics, at its best, listens carefully. It does not shout where it cannot hear. It waits for clearer signals, better instruments, and deeper connections. Recognizing where physics is silent does not weaken the reality described so far. It strengthens it by drawing honest boundaries. The solid world of experience, the predictive brain, the structured universe of fields and information all remain intact. What lies beyond those descriptions remains open, not empty, not arbitrary, simply not yet articulated. This openness is not an ending, it is a pause, a space where curiosity remains grounded, where speculation is tempered by discipline, and where the limits of knowledge are acknowledged without being dramatized. Reality does not become less real where physics is silent, it becomes quieter. And in that quiet, careful listening continues. Long before laboratories and instruments, questions about reality were already being asked. Philosophy began with a simple curiosity that remains familiar. What is the world really like beneath appearances? Can the senses be trusted? Is there something more stable behind the shifting surface of experience? These questions arose not from technology, but from reflection on ordinary life. One of the earliest and most influential figures to explore this was Plato. He suggested that the world encountered through the senses is not the most fundamental level of reality. In his famous allegory of the cave, shadows cast on a wall stand in for everyday experience, while the true forms that cast those shadows represent a deeper, more stable reality. The message was not that the world is false, but that appearance may not reveal structure fully. Plato's student Aristotle took a different approach. He emphasized careful observation of the natural world, arguing that reality could be understood by studying objects' causes and change directly. Forms, for Aristotle, were not separate from matter, they were embedded within it. This shift grounded inquiry in experience rather than abstraction, laying early foundations for empirical investigation. These two approaches set a tension that has never fully disappeared. Is reality something discovered through reasoning beyond the senses, or through systematic observation of the world as it appears? Philosophy explored both paths long before science formalized either one. During the early modern period, this tension sharpened. René Descartes famously questioned whether anything perceived could be trusted at all. He imagined a world in which senses might deceive completely. His goal was not to deny reality, but to find something indubitable upon which knowledge could be built. From this came the idea that certainty might begin in thought itself, rather than in perception. In contrast, philosophers such as John Locke and David Hume emphasized experience. They argued that knowledge arises from sensory input and reflection upon it. For them, the mind did not contain innate ideas about the world. It constructed understanding from interaction with it. This view aligned closely with later scientific methods, which prioritize observation and experiment. Immanuel Kant attempted to reconcile these positions. He argued that while knowledge begins with experience, it does not arise solely from it. According to Kant, the mind actively structures experience using built-in categories such as space, time, and causality. The world as it appears is shaped by the way the mind organizes information. Reality in itself, what he called the thing in itself, remains inaccessible. This idea resonates strongly with modern discussions of perception. Kant's insight was that experience is neither a direct copy of reality nor a free invention. It is a structured interface between mind and world. The mind contributes form, the world provides content. As science developed, these philosophical ideas did not disappear. They became embedded within scientific thinking itself. Early scientists were often philosophers as well. Isaac Newton described space and time as absolute structures underlying motion, reflecting metaphysical assumptions about reality. His laws worked extraordinarily well, even though their philosophical foundations would later be questioned. As physics progressed, philosophical reflection continued to shape interpretation. The emergence of quantum mechanics in the early 20th century forced scientists to confront questions about observation, measurement, and reality that had clear philosophical roots. Debates between figures such as Albert Einstein and Niels Bohr were not only technical, they were deeply philosophical disagreements about what physical theories say about the world. This brings us to a central distinction in modern philosophy of science. Realism and anti-realism are positions that attempt to clarify what scientific theories represent. Scientific realism holds that successful theories describe aspects of a mind-independent reality. When a theory works, It does so because it corresponds, at least approximately, to how the world truly is. Electrons exist, fields exist. Even if theories change, they converge toward truth. Anti-realism takes a more cautious stance. It suggests that theories need only be useful, predictive, and coherent. They do not need to be literally true descriptions of unobservable entities. From this perspective, electrons are tools within models rather than confirmed components of reality itself. Importantly, these positions are not simply opposites. Many philosophers adopt nuanced views that fall between them. Some argue that certain aspects of theories are real, while others are representational. Others suggest that realism applies at some scales but not others. What matters here is not choosing a side, but recognizing the role philosophy plays in clarifying assumptions. Science tells us how to build models and test them. Philosophy asks what those models mean. This distinction explains why philosophy and science address similar questions differently. Science focuses on prediction, measurement, and control. It asks what happens if certain conditions are met. Philosophy focuses on interpretation. It asks what it means for something to exist, to be known, or to be real. Neither replaces the other. Science advances by setting philosophical questions aside long enough to calculate and experiment. Philosophy advances by reflecting on what those calculations imply. Together, they provide depth and stability. Modern debates about reality continue this long conversation. Discussions about whether reality is observer-dependent, whether space-time is fundamental, or whether information underlies physics all echo earlier philosophical themes. The language has changed. The tools are more precise. The questions remain familiar. There is a quiet continuity here. When modern neuroscience asks how perception constructs experience, it revisits questions Kant raised about the mind's role in shaping reality. When physics debates the nature of measurement, it echoes arguments about appearance and reality that go back to Plato. Gentle humour fits naturally in noticing that philosophy has been asking the same questions for over 2,000 years, patiently waiting for better experiments. Science, in turn, keeps discovering that answering one question often reveals another. The value of philosophy in this context is not that it provides final answers. It provides perspective. It reminds inquiry to examine its own foundations. It keeps questions open without dissolving them into speculation. By tracing these roots, the modern discussion gains depth rather than confusion. The idea that reality might not be directly accessible is not a radical new claim. It is a refined version of a very old insight, now informed by neuroscience, physics, and careful measurement. Understanding this history helps steady the conversation. Questions about reality are not signs of crisis, they are signs of continuity. They show that curiosity about the nature of the world has always been part of human thought. The scientific picture developed so far does not float free of this tradition. It grows from it. Philosophy asked what reality is. Science learned how to test its answers. Together they continue to shape how reality is understood. Among all the things discussed so far, consciousness feels the most immediate. It is not something observed from the outside, it is something lived. Sounds are heard, colours appear, thoughts arise, emotions come and go. There is a sense of being present, of something it is like to experience the world. This subjective quality of experience is often called consciousness, and it sits at an unusual intersection between physics, biology, and philosophy. From a physical perspective, the brain is a material system. It is made of cells, chemicals, and electrical activity. Neurons fire, signals propagate, networks interact. All of this can be described using the language of biology and physics, yet none of these descriptions on their own seem to capture what it feels like to see red, to hear music, or to remember a childhood place. This gap has made consciousness one of the most challenging topics in science. Modern research approaches the problem carefully. Rather than asking what consciousness ultimately is, scientists ask what it does and how it behaves. Which brain processes correlate with conscious awareness? How does experience change when those processes are altered? What patterns of activity reliably accompany waking, dreaming, or deep sleep? One influential approach focuses on neural correlates of consciousness. This line of research aims to identify the minimal brain activity required for conscious experience. Studies using brain imaging, electrical recording, and stimulation show that consciousness depends on distributed activity across the cortex rather than on a single center. Damage to specific regions can alter experience, but awareness itself emerges from coordinated patterns. Another high-level theory is global workspace theory, developed by researchers such as Bernard Baars and expanded by others. This view suggests that consciousness arises when information becomes globally available across many brain systems. When a piece of information is broadcast widely, it enters awareness. When it remains local, it stays unconscious. This framework fits well with the idea of the brain as a predictive system. Conscious experience may reflect information that is especially relevant for updating models, guiding action, or resolving uncertainty. Awareness highlights what matters most at a given moment. A different approach is integrated information theory, associated with Giulio Tononi. This theory proposes that consciousness corresponds to the degree to which a system integrates information. According to this view, a conscious system is one whose internal states are both highly differentiated and highly unified. Experience arises from the system as a whole, rather than from individual components. Integrated information theory attempts to quantify consciousness in physical terms, linking experience to structure. While controversial and still debated, it represents a serious effort to bridge subjective experience and objective description. Other perspectives emphasize embodiment and interaction. Consciousness, from this view, is not confined to the brain alone. It arises from the ongoing relationship between brain, body, and environment. Sensory input, movement, and context all shape experience. Awareness is something that happens in action, not just in thought. Despite these advances, there are clear limits to current understanding. Science can explain many correlations. It can show how changes in brain activity alter experience. It can identify necessary conditions for consciousness. What it cannot yet explain is why certain physical processes are accompanied by experience at all, why there is something it is like to process information rather than nothing. This issue is sometimes called the hard problem of consciousness. The name reflects difficulty, not despair. It marks a boundary between what is currently explained and what remains open. Many researchers believe that continued progress in neuroscience will eventually clarify this gap. Others suggest that new conceptual frameworks may be required. What matters here is intellectual honesty. Consciousness is not ignored by science, but it is not solved either. Claims that it has been fully explained overreach. Claims that it is beyond all explanation give up too quickly. The reality lies in between. Linking consciousness back to perception helps keep the discussion grounded. Perception provides the content of experience. It fills awareness with colors, sounds, textures, and meaning. Prediction shapes what enters awareness and how it is interpreted. Memory gives experience continuity over time. Consciousness in this sense is not separate from the brain's modeling process. It is the lived aspect of that process. When the brain predicts and updates, some of the activity becomes conscious. When it operates efficiently in the background, it remains unconscious. Awareness may signal moments when models are being revised, decisions are being made, or uncertainty is high. This perspective does not reduce consciousness to illusion. It situates it within physical processes without denying its reality. Experience is real because it is happening. It is part of what the brain does. There is gentle humor in noting that consciousness, so often treated as mysterious, is also remarkably practical. It helps navigate the world, learn from mistakes, and coordinate complex behavior. Whatever its deeper nature, it plays a clear, functional role. Importantly, acknowledging the limits of explanation does not undermine the reality of experience. Pain hurts whether or not its nature is fully understood. Joy feels vivid regardless of theory. Consciousness does not require a final explanation to matter. From the broader perspective developed so far, consciousness fits naturally into an indirect view of reality. The brain builds models. Those models support perception and prediction. Consciousness is the subjective face of that modeling process. It is how the world, filtered and interpreted, shows up from the inside. Reality, then, includes both structure and experience. Physics describes patterns, interactions, and constraints. Neuroscience describes mechanisms and correlations. Consciousness describes what it is like when those mechanisms are active in certain ways. These descriptions do not compete. They address different aspects of the same system. Understanding this allows consciousness to be discussed without exaggeration. It is neither a magical substance outside physics nor a trivial byproduct to be dismissed. It is a phenomenon rooted in physical systems that has not yet been fully mapped. The quiet lesson here is consistency. The same themes appear again: indirect access, modeling, interaction, emergence. Consciousness does not stand apart from these ideas. It exemplifies them. Experience feels immediate and personal, yet it arises from processes shaped by evolution, physics, and history. The brain inside the world it models gives rise to a world inside experience. Science continues to explore this relationship carefully, piece by piece. What is known grows steadily. What is unknown remains acknowledged. Consciousness remains one of the most intimate features of reality, not because it escapes the physical world, but because it is how the physical world becomes present from within. The word illusion carries weight. In everyday language, an illusion suggests something false, a trick, a mistake, a mismatch between appearance and reality, where what is seen is not really there. When used carelessly, the word can imply deception or unreliability, as though experience itself cannot be trusted. In science, the meaning is more precise and far less dramatic. An illusion is not a false experience. It is a lawful outcome produced by normal perceptual processes operating under particular conditions. The experience is real. What differs is the relationship between the experience and the physical situation that produced it. This distinction matters. When a straight line appears bent in a visual illusion, the bending is genuinely experienced. The brain is not pretending. It is applying learned rules about depth, perspective, and lighting. The illusion reveals how perception works, not that perception is broken. Seen this way, illusions are windows into construction, not evidence of failure. This careful definition helps clarify what it means to ask whether reality itself is an illusion. If illusion means falsehood, then the answer is straightforward. Reality is not an illusion. The world pushes back. Objects resist pressure. Heat burns. Gravity pulls. Physical laws constrain outcomes regardless of belief. If illusion means constructed experience, the answer becomes more nuanced. Experience is constructed. Perception does not present reality in its entirety. It filters, predicts, and interprets. The brain delivers a usable version of the world shaped by biology, history, and context. This construction is not optional. It is how perception functions. Calling this an illusion without explanation can be misleading. It suggests that nothing is real or that experience is arbitrary. Neither is true. Neuroscience shows that perception is indirect but reliable. Predictive processing explains how expectations and sensory input combine to produce stable experience. Errors occur, but they are constrained by the physical world. The brain cannot simply invent a reality disconnected from interaction. Physics reinforces this grounding. At different scales, reality behaves differently, but it remains structured and lawful. Atoms, fields, and space-time follow consistent rules. Measurement interacts with systems, but does not create them. Information flows are constrained by energy and entropy. Nothing in physics suggests that the world is imaginary or optional. The apparent strangeness arises when everyday intuition is applied beyond its domain. Human experience evolved to represent a world of objects, surfaces, and motion. When science probes beyond that scale, the underlying structure no longer matches intuition. This mismatch can feel unsettling, but it does not imply illusion in the sense of falsehood. A useful comparison is a map. A map simplifies reality. It omits details. It distorts scale. It emphasizes certain features over others. None of this makes the map deceptive. It makes it useful. A subway map does not show the precise geography of a city. It shows connections that matter for navigation. Experience functions in a similar way. It is a map, not the territory. Calling the map an illusion misses the point. It is accurate in the ways that matter for its purpose. This perspective helps integrate neuroscience and physics without conflict. The brain builds models. Physics describes structure. Experience is where those models meet the world. Neither side negates the other. The constructed nature of perception does not undermine the existence of an external reality. It explains how that reality becomes accessible. There is gentle humor in noticing that experience feels most real precisely when its construction is invisible. The brain works hardest to hide its own work. When everything functions smoothly, perception feels direct. When something breaks down, as in an illusion, the scaffolding briefly appears. This does not mean that reality disappears when looked at closely. It means that the interface becomes visible. Calling reality an illusion can therefore be useful only if the term is carefully framed. It can highlight that experience is not a direct imprint of the world. It can remind that intuition has limits. It can encourage humility about perception. Without that framing, the term creates confusion. Reality is not a hallucination. It is not a simulation in the everyday sense. It is not dependent on belief. It has structure, regularity, and constraint. Experience does not replace reality. It responds to it. At the same time, experience does not reveal reality in full. It reveals a version shaped by prediction, interaction, and scale. This version is neither false nor complete. It is sufficient. The tension dissolves when illusion is understood as interface rather than error. Perception is a biological interface between organism and environment. Physics provides a mathematical interface between measurement and structure. Neither captures everything, both capture enough. This prepares the ground for synthesis rather than resolution. There is no final moment where illusion is stripped away to reveal pure reality. There is no hidden layer where experience suddenly becomes direct. Understanding grows by layering perspectives, not by discarding them. The solid world of daily life remains valid. The probabilistic world of physics remains accurate. The predictive brain remains effective. These descriptions coexist. The question is not whether reality is an illusion. It is what kind of access is available. Science suggests that access is indirect but reliable. Philosophy reminds that interpretation matters. Neuroscience explains how models are built. Physics explains what constrains them. Together they point toward a calm conclusion. Reality is not hidden behind illusion. It is encountered through construction. The experience of a world is real. The world that shapes that experience is real. The relationship between them is structured, lawful, and incomplete. Illusion, understood properly, is not a threat to reality. It is a clue to how reality is known. After so much careful questioning, something steady remains. Not everything dissolves when perception is examined. Not everything shifts when scale changes. Not everything becomes uncertain when interpretation is acknowledged. Beneath the layers of construction, modeling, and approximation, there are features of reality that remain remarkably stable. One of these is regularity. Events follow patterns. Causes lead to effects. Similar conditions tend to produce similar outcomes. This regularity is what allows prediction at all. It is why habits form, why tools work, and why learning is possible. Without regularity, experience would fragment into noise. This regularity persists across scales. At human scales, objects fall, collide, and endure. At microscopic scales, particles interact according to consistent probabilities. At cosmic scales, stars form, burn, and evolve following predictable pathways. The details change, the presence of pattern does not. Closely related is causation. While the interpretation of cause and effect can become subtle in advanced physics, the basic constraint remains. Changes do not occur without reason. Physical processes unfold according to lawful relationships. Energy flows, momentum transfers, information propagates. Nothing appears from nowhere without accounting. Even in quantum physics, where outcomes are probabilistic, causation is not abandoned. Probabilities are determined by well-defined rules. Experiments do not produce arbitrary results. They produce distributions that can be predicted and tested. Uncertainty exists within structure, not in place of it. Constraint is another feature that remains solid. Reality does not permit everything. There are limits. Objects cannot exceed certain speeds. Energy must be conserved. Processes must obey symmetry principles. These constraints are not preferences. They are boundaries enforced by the structure of the physical world. Conservation principles are especially important here. Conservation of energy, momentum, and charge remain valid across an enormous range of conditions. They survive changes in theory and interpretation. Even when new frameworks replace old ones, these principles are usually preserved in deeper form. This robustness explains why mathematics continues to work so well. Mathematics does not describe appearances. It describes relationships. When those relationships are stable, mathematical models remain effective even as interpretations evolve. The same equations can be understood differently, while continuing to predict outcomes accurately. Measurement builds on this stability. Even when perception is indirect and instruments interact with systems, measurements converge. Independent methods agree. Standards remain fixed. Repeatable experiments produce consistent results. This consistency does not depend on how reality is imagined. It depends on how reality behaves. The success of repeatable experiment is one of the strongest indicators that something solid is being captured. If reality were fundamentally illusory in the sense of being arbitrary or unconstrained, such agreement would be impossible. The fact that experiments work over and over again across cultures and centuries speaks to deep regularity. This does not require knowing everything. Scientific humility plays an important role here. Recognizing what remains solid does not require claiming complete understanding. Physics can admit uncertainty about quantum gravity while relying confidently on thermodynamics. Neuroscience can explore consciousness without doubting basic brain function. Cosmology can question origins while accurately describing expansion. Knowledge is layered. Confidence applies within domains. Uncertainty marks boundaries rather than undermining foundations. This layered confidence is often misunderstood. Admitting limits is sometimes mistaken for weakness. In science, it is the opposite. Clear boundaries protect reliable knowledge from being overstated. They allow progress without collapse. There is a quiet strength in this approach. It allows one to say, with confidence, that the world behaves lawfully, even while admitting that some aspects are not yet explained. It allows one to trust experience where it works, without mistaking it for a complete account. It allows theories to be revised without discarding everything that came before. From this perspective, indirect access to reality becomes less troubling. If perception were indirect in a chaotic world, nothing could be trusted. In a structured world, indirect access can still be reliable. Interfaces work because what they interface with is stable. Maps are useful because the terrain does not rearrange itself arbitrarily. The brain's models succeed because the world they model is constrained. Prediction works because patterns persist. Learning accumulates because history matters. Even uncertainty itself is bounded. Probability distributions follow rules. Error ranges can be estimated. Unknowns can be categorized. This is not vagueness. It is structured ignorance, surrounded by islands of certainty. There is gentle humor in realizing that reality does not require full understanding to cooperate. Bridges stand whether or not quantum gravity is solved. Medicines heal without a final theory of consciousness. Clocks tick reliably despite unresolved questions about time's origin. This reliability is not accidental. It reflects deep order. What remains solid, then, is not a particular picture of reality, but its behavior. Reality responds consistently to interaction. It resists in predictable ways. It rewards careful inquiry with usable answers. This recognition shifts the emotional tone of the discussion. Rather than ending in doubt, it ends in grounded confidence. Not confidence in having final answers, but confidence in the process that produces increasingly good ones. Not certainty about ultimate nature, but trust in structure. The earlier questioning served a purpose. It cleared away assumptions of directness without dissolving substance. It showed how perception, modeling, and theory shape experience without disconnecting it from the world. What remains is a calm understanding. Reality does not owe complete transparency. It offers regularity. It offers constraint. It offers patterns that can be learned, tested, and relied upon. This is enough. It is enough for science to function. Enough for experience to feel coherent. Enough for knowledge to grow without claiming finality. The solid ground beneath all this questioning is not an object or a picture. It is a set of relationships that hold steady even as understanding deepens. Reality, approached carefully, proves to be resilient. That resilience is what allows inquiry to continue with confidence rather than anxiety, curiosity rather than fear. The world does not dissolve when examined closely. It holds. Reality did not begin with observers. Long before eyes opened or minds reflected, the universe was already unfolding. Stars formed, galaxies collided, particles interacted, and space-time expanded without anyone there to notice. This simple fact quietly reshapes the question of what reality is. Whatever reality may be, it does not depend on being experienced in order to exist. Physics models this unobserved universe with remarkable confidence. Cosmology describes events that occurred billions of years before life appeared. According to current understanding, the universe began in a hot, dense state and expanded rapidly. As it cooled, simple particles formed, then atoms, then stars and galaxies. These processes unfolded over immense spans of time, guided by physical laws that operated without reference to consciousness. One of the strongest pieces of evidence for this early history is the cosmic microwave background. This faint radiation fills all of space and represents light released when the universe was young, roughly 380,000 years after its beginning. It carries information about temperature variations that later grew into galaxies and clusters. No observer witnessed this moment. Its traces remain nonetheless. This radiation was not created for minds to interpret. It exists because physical processes occurred. Instruments built much later detected it. Analysis revealed its meaning. The universe left a record of itself long before anyone was around to read it. This distinction is important. Observation by instruments is not the same as experience by minds. A satellite measures radiation through interaction between matter and energy. It does not feel wonder or curiosity. It does not experience the data. It simply responds according to physical laws. The data exists independently of how it is later interpreted. This reinforces a key point. Reality does not require awareness to function. Processes unfold, interactions occur, patterns develop. Observation, in the scientific sense, is a way of accessing information about those processes after the fact, not a condition for their existence. Deep time makes this especially clear. The Earth formed over 4 billion years ago. For most of its history, it hosted no conscious life. Mountains rose and eroded, oceans formed and shifted, magnetic fields waxed and waned. All of this happened without experience. The rocks did not need to be seen to cool. The tides did not need to be felt to move. Even biological evolution proceeded for billions of years before nervous systems emerged. Life responded to chemical gradients, sunlight, and competition long before it developed awareness. Natural selection shaped organisms through interaction alone. Experience arrived late in the story. This does not diminish experience. It places it in context. Consciousness is a recent development in a very old universe. It is a way reality has learned to reflect upon itself locally. It is not a prerequisite for structure, law, or persistence. This perspective widens the frame. When discussing perception and modeling, it is easy to become centered on the human viewpoint. Experience feels primary because it is familiar. Stepping outside that viewpoint reveals that reality has been operating just fine without it. Physics handles this shift naturally. Its models do not include observers unless observers are part of the system being modeled. Stars evolve according to nuclear processes. Galaxies form through gravity. Expansion follows from space-time geometry. These descriptions remain valid whether or not they are being contemplated. This is not a claim that reality is fully captured by equations. It is a claim that reality is not dependent on minds for its existence. There is sometimes confusion here, especially when discussing measurement in quantum physics. The term observer can misleadingly suggest consciousness. In practice, observation refers to interaction. A particle interacting with a detector is an observation. A photon striking a sensor is an observation. No awareness is involved. This distinction preserves consistency. Reality can exist independently of minds while still requiring interaction for information to be extracted. Instruments do not experience reality, they register it. Minds then interpret those registrations. Experience enters only at the final stage. Understanding this helps prevent a common misunderstanding. The indirect nature of perception does not imply that reality is mind-dependent. It implies that access to reality is mediated. The thing accessed remains. There is gentle humor in realizing that the universe waited billions of years before producing anything capable of worrying about whether it was real. It expanded, cooled, and structured itself patiently, unconcerned with interpretation. This does not make human inquiry insignificant. It gives it perspective. Science becomes a way of listening to a story that began long before the listener arrived. Instruments extend senses beyond their limits. Mathematics organizes patterns. Models reconstruct events that left traces. Knowledge accumulates without needing to be present at the beginning. This approach relies on consistency. If reality behaved differently when unobserved, reconstruction would be impossible. The success of cosmology depends on the assumption that physical laws apply universally and continuously, regardless of observation. So far, this assumption has worked extraordinarily well. The cosmic microwave background matches predictions. Stellar life cycles align with models. Element abundances reflect early nuclear processes. The universe appears to have followed the same rules before life as it does now. This continuity is stabilizing. It suggests that reality is not a fragile projection sustained by awareness. It is a robust process that unfolds according to structure and constraint. Minds emerge within it, not above it. From this widened view, earlier discussions gain clarity. Perception is indirect because it is a late arriving interface. Modeling is necessary because access is mediated. Consciousness reflects reality from within rather than creating it. Reality without humans is not empty or meaningless. It is simply unexperienced. Meaning enters with minds. Structure does not require it. This distinction allows both to coexist without conflict. The universe does not need to be perceived to exist. Experience does not need to create reality to matter. Each occupies its own role. By stepping back beyond the human viewpoint, the discussion relaxes. The pressure to make experience foundational eases. Reality can be allowed to be what it is, vast, structured, and largely indifferent to interpretation. From within that vastness, experience arises briefly, locally and meaningfully. This is not a demotion of consciousness. It is an expansion of context. Reality continues whether or not it is watched. When it is watched, something remarkable happens. The universe becomes aware of itself, if only in small pockets. That awareness does not define reality. It participates in it. The perspective widens. The ground remains steady. Science does not aim to copy reality. It aims to model it. A scientific model is a structured representation that captures certain features of the world while ignoring others. It highlights what matters for a given purpose and sets aside what does not. In this way, a model functions much like a map. It is not the territory itself. It is a guide that helps navigate it. This distinction is essential. A map of a city does not include every brick, leaf, or crack in the pavement. It simplifies scale. It distorts distance. It uses symbols instead of buildings. None of this makes the map wrong. It makes it usable. The value of the map lies in how well it supports movement, orientation, and prediction. Scientific models work in the same way. They compress complexity into manageable form. They describe relationships rather than appearances. They succeed not by resembling reality visually, but by allowing reliable inference. History provides many clear examples of this process. Early models of the solar system placed Earth at the center, with planets moving in complex paths around it. These models were wrong in their central assumption, yet they still produced useful predictions. Later, heliocentric models replaced them, simplifying the structure while preserving much of the predictive machinery. The shift did not erase prior progress, it refined it. Similarly, classical mechanics describes motion with great accuracy at everyday scales. It predicts the paths of projectiles, the motion of machines, and the orbits of planets to a high degree of precision. When relativity and quantum physics emerged, classical mechanics was not discarded. Its domain of validity was clarified. The same equations still work where they always worked. They were not false, they were incomplete. This pattern repeats across science. Models evolve, new layers are added, old frameworks are absorbed rather than destroyed. Progress looks less like replacement and more like nesting. Misunderstandings arise when models are mistaken for literal pictures of reality. When atoms were first modelled as tiny solar systems with electrons orbiting nuclei like planets, the image was useful but misleading. It helped organize early understanding, but it was never meant to be a faithful depiction. As quantum theory developed, that picture gave way to probabilistic descriptions that no longer resemble everyday objects at all. The earlier model was not wrong because it failed to look like reality. It was wrong because it failed to predict certain outcomes. Visual resemblance was never the standard. Predictive success was. This confusion persists today. When people imagine scientific models as claims about what reality really looks like, disappointment often follows. Quantum fields, curved space-time, and probability amplitudes do not resemble ordinary experience. Expecting them to do so misunderstands their purpose. Models are tools, not mirrors. Usefulness, prediction, and internal consistency matter more than intuitive comfort. A model that feels strange but predicts accurately is more valuable than one that feels familiar but fails. This perspective also explains why multiple models can coexist. Different models may describe the same system at different scales or for different purposes. A fluid can be modelled as a continuous substance or as a collection of molecules depending on what is being studied. Neither description cancels the other. Each highlights different features. Confusion often arises when a model is elevated to the status of reality itself. When people say that reality is nothing but information, or nothing but mathematics, or nothing but perception, they often mistake a powerful description for an exclusive claim. Each of these frameworks captures something real. None exhausts the whole. This mirrors what happens in perception. The brain builds internal models of the world. These models allow navigation, prediction, and action. They are not copies of reality. They are interfaces. When perception works well, the difference between model and world becomes invisible. When it fails, the distinction briefly appears. Illusions reveal this process. So do errors, surprises, and learning. The brain updates its models when predictions fail, just as science updates its theories when experiments disagree. The same humility applies at both levels. Perceptual models are trusted because they usually work, not because they are complete. Scientific models are trusted for the same reason. Their success lies in constraint and reliability, not in finality. There is gentle humour in noticing that disappointment with science often comes from asking it to do something it never promised. Science does not promise ultimate pictures. It promises workable ones. Understanding models as maps dissolves many unnecessary tensions. It becomes clear why theories can change without knowledge collapsing, why deeper explanations do not invalidate surface ones, why indirect access to reality does not undermine confidence. Reality does not need to be perfectly represented to be navigated effectively. What matters is that models stay aligned with how the world behaves. This alignment is maintained through testing, comparison, and revision. Models that fail are adjusted or abandoned. Models that succeed are refined. Over time, understanding grows more precise without pretending to be complete. Returning to the theme of perception brings the discussion full circle. The brain inside the world it models builds maps that are good enough to survive and act. Science is an extension of this same process, using instruments and mathematics instead of nerves and muscles. Both rely on abstraction. Both trade completeness for clarity. Mistaking models for reality leads to confusion. Recognizing them as tools restores balance. Reality is not hidden behind models, it is approached through them. Maps do not replace landscapes, they help navigate them. Scientific models do not replace reality, they help understand it. When this is kept in mind, misunderstanding fades, confidence remains, inquiry continues without the pressure to find a final picture. The world stays solid, the maps improve. Living in an indirect world sounds at first unsettling. If experience is constructed, if perception filters and predicts, if models stand between mind and matter, it can feel as though something important has been lost, as though certainty has slipped away, as though the ground beneath everyday life has become unstable. In practice, the opposite is true. Understanding that access to reality is indirect does not weaken experience. It explains why experience works as well as it does. It replaces a fragile idea of directness with a more durable idea of reliability. Daily life depends on trust. Trust that the floor will support weight. Trust that other people are real and responsive. Trust that memories usually correspond to events that occurred. None of this requires perfect access to reality. It requires consistency. It requires that the world behave in ways that match expectations often enough to act confidently. Indirect perception delivers exactly that. The brain's models are shaped by millions of interactions. They are tested constantly. Predictions that fail are revised. Over time, this produces a working relationship with the environment that is stable, flexible, and resilient. Experience does not need to be exact to be meaningful. It needs to be dependable. Recognizing this can quietly reduce anxiety. If perception were supposed to be a flawless mirror of reality, every illusion or error would be a threat. Understanding perception as a construction reframes these moments. Errors become part of the process rather than evidence of deception. They are signals for adjustment, not signs of collapse. Meaning is not diminished by this understanding. Meaning arises from relationships, values, and shared patterns, not from perfect representation. A conversation matters because it affects people, not because it captures reality in total detail. A decision matters because it leads to consequences, not because it rests on absolute certainty. Indirect access does not make choices arbitrary, it makes them contextual. Decision-making has always involved uncertainty. The brain evolved to act under incomplete information. Prediction, risk assessment, and learning are built into its operation. Acknowledging this does not introduce instability. It clarifies what has always been the case. Science and technology depend on the same principle. No scientific model is complete. No measurement captures everything. Yet technologies work. Bridges stand, medicines heal. Navigation systems guide aircraft across continents. These achievements rely on shared approximations of reality that are good enough, stable enough, and consistent enough to coordinate action. This coordination is crucial. Modern life depends on cooperation at vast scales. People who have never met rely on the same measurements, standards, and models. Time zones align. Electrical systems synchronize. Communication networks function. None of this requires anyone to perceive reality directly. It requires agreement about how reality behaves. That agreement is earned through repetition and correction. Shared models are not imposed by belief. They are negotiated through evidence. When something stops working, it is revised. When it continues to work, it is trusted. This pragmatic grounding keeps abstraction tethered to consequence. Understanding indirect reality can therefore strengthen trust rather than weaken it. Trust shifts from the idea that experience is a perfect copy to the idea that experience is a reliable guide shaped by interaction. This is a quieter, more stable form of trust. It does not demand certainty. It tolerates error. It improves with feedback. There is emotional grounding here. The world does not need to be perfectly known to be lived in fully. Familiar places still feel familiar. Relationships still matter. Beauty still appears. Pain still hurts. Joy still arrives unexpectedly. None of this is undone by knowing that experience is constructed. If anything, it becomes easier to be gentle with experience. Moments of confusion or misinterpretation are no longer personal failures. They are part of how cognition works. Disagreement does not imply that reality has fractured. It reflects differences in perspective, information, and context. This perspective also encourages humility. If access to reality is indirect, then certainty should be proportional. Strong claims deserve strong evidence. Doubt becomes a tool rather than a threat. Curiosity becomes safer because it no longer risks pulling the floor away. There is gentle humor in noticing that human life has always proceeded this way. People built civilizations, navigated oceans, and explored space long before fully understanding perception or physics. Indirectness did not stop progress. It enabled it. What changes with understanding is not function, but attitude. The need for absolute answers softens. The pressure to resolve every question fades. In its place grows confidence in process, trust in correction, appreciation for structure. Living with an indirect world also deepens connection. Shared reality is not something passively received. It is something actively maintained. Language, measurement, science, and culture all participate in aligning individual experiences into something coherent. Meaning emerges through this alignment. This makes cooperation more impressive, not less. Millions of separate minds, each with indirect access, manage to agree enough to build, teach, explore, and care for one another. The success of this coordination is one of the strongest arguments that reality, while indirectly accessed, is not unstable. The world resists, it constrains, it responds. That response is what holds everything together. As the narrative approaches synthesis, the emotional tone naturally shifts. The earlier chapters explored limits, uncertainty, and construction. This chapter rests with their implications. Indirect access does not trap anyone inside illusion. It situates experience within a structured world that can be learned, shared, and trusted. Reality does not need to be fully transparent to be dependable. It needs to be consistent enough to support life, learning, and cooperation. So far, it has done that extraordinarily well. Living with an indirect world becomes less about doubt and more about orientation, knowing where certainty applies, knowing where openness remains, knowing that neither undermines the other. The world remains solid underfoot, experience remains meaningful, inquiry remains worthwhile. The indirect nature of access is not a problem to be solved, it is a condition to be understood, and once understood, it settles quietly into the background, allowing attention to return to living, learning, and connecting within a reality that continues to hold. At the end of this long path of questioning, the picture that remains is quieter than expected. Reality did not dissolve. Experience did not become meaningless. The world did not slip away when examined closely. Instead, something more stable came into view, a recognition that life is lived inside models, and that this has always been the case. The brain builds representations because it must. It cannot take in everything at once. It cannot step outside the world to see it whole. So it predicts, filters, and interprets. It constructs a version of reality that is usable, coherent, and responsive to action. This version is not a deception. It is a working interface shaped by evolution and experience. Physical reality provides the structure that makes this possible. The world behaves lawfully, events follow patterns, interactions leave traces, constraints hold. Even when theories change and interpretations shift, regularity remains. Physics captures aspects of this structure with remarkable success, even while openly acknowledging its limits. What is known is substantial. Objects persist, forces operate, energy is conserved, time orders change, information flows, instruments agree, experiments replicate. The universe existed long before minds appeared and continues regardless of observation. These facts do not depend on interpretation. They are supported by evidence and reinforced by consequence. What remains uncertain is equally important. The deepest nature of consciousness is not yet explained. The union of quantum physics and gravity is incomplete. The origin of the universe's initial conditions remains open. These gaps do not undermine what is known. They define the edges of current understanding. Uncertainty in this sense is not a flaw. It is a boundary marker. It shows where curiosity should remain active and where humility is appropriate. Living inside a model does not mean being cut off from reality. It means engaging with reality through structured approximation. Maps guide movement without claiming to be landscapes. Models support understanding without claiming to be final. Perception works because the world it interfaces with is stable. Science works because that stability extends beyond individual experience. Shared methods, measurements, and corrections align separate perspectives into a coherent picture. This coherence is not fragile. It does not require perfect certainty. It requires consistency. It requires openness to revision. It requires respect for evidence. These conditions have been met often enough to build knowledge that endures and technologies that function. The emotional tone of this understanding is not disruption. It is reassurance. Nothing important is taken away by recognizing that experience is constructed. The warmth of sunlight remains. The solidity of the ground remains. Meaning remains where it has always been, in relationships, values, and shared understanding. If anything, the pressure to find ultimate answers eases. Reality does not demand full resolution in order to be lived within. It allows partial understanding. It rewards careful inquiry. It remains structured whether or not it is fully grasped. There is comfort in this. The universe does not rush explanation. It unfolds. Knowledge accumulates gradually. Models improve. Old ideas are refined rather than erased. Understanding deepens without requiring finality. Living inside a model becomes less about limitation and more about participation. Each perception, measurement, and theory is a way reality engages with itself. Minds are not separate observers standing apart. They are physical processes within the world, reflecting local patterns of a much larger structure. Understanding this places experience back where it belongs, not outside reality, questioning whether it is real, but inside reality, learning how it behaves. The world does not need to be fully revealed to be trusted. It only needs to be consistent enough to support life, learning, and care. So far it has done exactly that. The final lesson is simple and steady. Understanding reality does not require resolving it completely. It requires recognizing what is solid, respecting what is unknown, and remaining open to revision without fear. The model holds, the world responds, experience continues, and within that continuity, curiosity can rest without needing to resolve everything it touches.